Well, welcome everybody. Thank you for joining us today, which is an amazingly exciting seminar on sustainable composite materials for wind turbine blades. This seminar is brought to you by a collaboration between the University of Bristol and its Bristol Composites Institute and the Offshore Renewable Energy Catapult, which is a UK government organisation. And together, through a 5-year funded venture called the Windblade Research Hub, we're investigating research of material science, structures and manufacturing in future wind turbine blades. So I'll show you the agenda for today. We have a packed schedule. Please keep your Q&A and comments coming in the usual Zoom functionality. In the first session, there will not be time for verbal Q&A, but we will endeavour to do our best for the speakers to address questions through the chat. 2 technical sessions today. I'll be chairing the event until 20 to 3, and then my colleague, Dr. Mark Forrest of Offshore Renewable Energy Catapult, will be taking over from them. And then we'll conclude proceedings with an industrial panel discussion led by Professor Steve Eichhorn. So who am I? I'm Paul Weaver. I'm chair in lightweight structures at University of Bristol, and also the Benel chairing in composite materials and their structures at University of Limerick. I've been working in wind turbine blade design for around 20 years with Vestas and the forerunners of Vestas in the UK. And at Bristol, we led a preferred partnership in composite technologies with Vestas for a number of years. And since 2017, we've hosted the Windblade Research Hub at Bristol in conjunction with Offshore Renewable Energy Catapult. So after me, I'll introduce Dr. Steve Wyatt from ORE Catapult. And we have 2 industrial speakers to kick off events with, Mie Elholm Birkbak and Harald Stecher from Vestas and Siemens Gamesa, respectively. So what is the main issue here? It's really simply put. We have to avoid this scenario. It's an anachronism. This headline from National Paper in Ireland called it Clean Energy's Dirty Little Secret. So what you're looking at here are these wind turbine blades at the end of their useful life or perceived useful life, and with no value, they're just being buried. It's never mind the elephant in the room, it's the elephant's graveyard. It's a terrible thing. And the materials in these blades are typically organic and derived from, a lot of them derived from oil-based products. So we need to move to a situation as soon as possible, whereby we get as much value out of these oil-based products, or ideally move away from oil-based products to plant-based materials, structural materials, which is possible and viable. And these are sort of topics that are going to be addressed by both industry and academia in today's session. After we do the first industrial session, the agenda will proceed with a technical session with presentations by Steve Eichhorn, with an expert on cellulosic materials, and parallel to that is Maurice Collins on lignin fibres. And then from the Offshore Renewable Energy Catapult, we have Dimitrios Mamalis, who'll be talking about the novel thermoplastics. Then the second technical session will have various representatives from the National Composites Centre, another catapult centre based in Bristol, Darshil Shah on biocomposite blades, and then we have more material science aspects from Ian Hamerton from Bristol Composites Institute on matrix fibre modification. And then with a company perspective, ORE Composites in Ireland, we have Tomas Flanagan discussing their work on manufacture and testing of large composite structures, including wind turbine blades. In the 2 technical sessions, we'll have up to 10 minutes for verbal Q&A with speakers, as well as doing it through the chat. And we endeavour to have 5 10-minute breaks in each session. So with that, I want to pass on to Steve Wyatt, who's Director of Research and Disruptive Innovation at the Offshore Renewable Energy Catapult. The floor is yours, Steve, and I will stop sharing.
Well, thank you so much for that. I will just pull up a few slides to share. So hopefully you can all see that. Is that coming across okay? I'll take silence as yes. Please shout if it's not.
We can see your presenter view, so you might want to share the slideshow mode.
Or switch the display settings to the other screen.
How's that? Is that better?
Yes.
Perfect. Okay. Well, thanks very much, and well, good afternoon, everyone. It's fantastic to see so many people online. So really, thanks for making the time in your calendars to tune into this really important seminar. As has been said, I'm Steve Wyatt. I'm the Director of Research and Innovation at ORE Catapult. So I'm responsible for our internal research program as well as much of our externally facing research activity. I've just got a handful of slides to sort of frame an introduction to this afternoon's seminar. Some of you in the audience may be wondering, hopefully some of you are wondering actually, who are ORE Catapult, because we're trying to reach people beyond our normal ecosystem here. So ORE Catapult, Offshore Renewable Energy Catapult, we are one of 9 catapult centres set up in the UK, partly funded by UK government. And our job, put simply, is to accelerate great innovative technology developed by UK companies. And so we have a range of technical experts on our staff, and also a range of unique assets, particularly large-scale testing assets, to help with the evaluation and development of technologies, and technologies such as blades, drivetrains, etc. We also have a demonstration turbine that we put new innovative technology on that you wouldn't dare put onto an operational wind farm. And I guess we measure our success, or we've historically actually measured our success in 2 ways. One is how are we driving down the cost of electricity generated from offshore renewables? And secondly, are we creating great UK benefit? And I'd argue perhaps that increasingly we are beginning to think about our industry's sustainability credentials. And obviously we're going to talk a bit more about that today. Of course, the key thing here is what is happening to the offshore wind market. And we're in this really excellent position at the moment where offshore wind are the darlings of the net zero transition. Offshore wind's been described as the backbone to low carbon energy. And indeed, it's the lowest cost way of generating large scale electricity. The PM likes it because it's creating jobs. The Committee on Climate Change like it because we're going to drive to net zero using it. And of course, the UK are leading the way in this. And so the broader government like it because it underpins the export strategy. So against that political backdrop, we're seeing huge amounts of offshore wind being developed. Here's a map. The bubbles there indicate the size of the offshore wind farms being developed. The dark ones, the dark colours, the dark purples are operational. The orange bubbles there are the ones that are in planning. And you'll see there is a huge amount of offshore wind being developed over on the east coast, beginning to do offshore wind over on the west coast there, just in North Wales. And if you add floating wind to this, you see large tracts of sea being opened up on the southwest approaches and up off the coast of western Scotland as well. And the headline is that offshore wind is going to quadruple from where we are today in the next decade. So we're going to have 40 gigawatts of offshore wind, 4 times what we have today in the next decade. And the main reason for this is, of course, the cost reduction journey that you can see on the chart there. So that's all great. So what is there not to like about offshore wind? And by the way, isn't it green enough already? Why are we even questioning the green credentials of offshore wind? Well, I mean, the answer is we are a significant industry. We're set to become an even bigger industry. And we absolutely need to be looking at our environmental credentials in the same way a fast fashion brand would look at their environmental credentials. We cannot escape the fact that our turbines have huge amounts of embedded carbon in. We have challenges around decommissioning. And we really need to understand our end-to-end environmental impact, whether that's the balsa wood that's in the blades, whether it's the steel and concrete in the foundations, or indeed the composite materials that are providing the structural integrity to our rotor. So all of that absolutely needs to be dealt with. And we started looking at numbers some time ago for this when we thought this had to be a research priority for our research hub. And if you just look at the amount of wind turbines that are going to be decommissioned in the next period, well, by 2050, we're going to have 85 gigawatts of offshore wind decommissioned. So there's going to be 75 gigawatts of broadly operational, but we would have decommissioned more than we have operational by that time. And 1,200 gigawatts of onshore wind capacity. So on a global basis, this really is the elephant in the room, as Paul said. And yeah, this is a genuine picture from the US where they are literally burying wind turbine blades. And we're told they're doing this until we have a better way of recycling them. But crikey, we are filling the land with these wind turbine blades. Mark Forrest, who you'll hear from later on, was running some numbers for me on tonnage. And he was saying, well, by 2050, we'll have 56,000 tons of GRP from wind turbine blades that we need to do something with. And another 6 years later on, that will double, and then it will double again. And so we have this tremendous mounting up. I mean, the good news is we do have eyes on this problem, and we do have significant research going on, looking at better ways of decommissioning the existing fleet, but also importantly, looking at how we engineer in much better sustainability credentials from the outset. So how can we change the way we're engineering resins such that they can lend themselves to much more effective recycling? How can we recover fibers more effectively, etc.? And how can we look at entirely different manufacturing processes that mean we're using less material from the outset, but also we're setting ourselves up to much better reclamation of the materials at the end of their life. And I guess finally, I'll also just sort of point to the fact we're not alone in this. This is an issue that the automotive industry have been grappling with, the aerospace industry have been grappling with. So there are other significant industries out there, all of which want to see solutions here. So if you're a potential solution provider in the audience today, this isn't just about offshore wind. There are other big markets as well. And what we're hoping to do through the research hub is pull together that Composites knowledge to make sure we've got the best chance of cracking this problem. So I'll leave it there. Thanks very much for listening to that little intro. Hopefully that's kind of just set the scene a little bit. Big problem. And hopefully we'll have a great opportunity to talk about these issues this afternoon. So thanks for that, and back to you, Paul.
That's a great introduction, Steve. Much appreciated. Thanks. Don't be shy, delegates. Put your Q&A in the chat for Steve. He can address them as we go through the next presentations. But for the time being, thanks, Steve. And we'll move on to our first industrial perspective speaker. And it's a delight to introduce to you Mie Birkbak, who's a specialist in innovation and concepts at Vestas Wind Systems. And she's going to discuss the CeTeC project and development of a new sustainable epoxy system. Mie, the floor is yours. Please share your screen when you are ready.
Yeah, thank you so much. And thank you also to coming after this overall introduction, because I think it captures very well sort of the challenge we are standing in front of. And do you see my screen now?
Everything's perfect. Thank you, Mie.
Well, so I think most of you in the session here will know Vestas. We are, as you said, a producer of wind turbines. We have put up more wind than anyone else. And that also means that we are present in more than 80 countries around the globe. And in Vestas, we're of course very happy to put up all this wind, but we also have some quite ambitious goals, both in terms of being completely carbon neutral within 2030, and also having zero waste by 2040. And that leaves us in front of this challenge, as you just addressed also, that especially the blades of the rotor are challenging to get hold of. So I hope after this day today, I think we can all be on the same page that we are standing in front of a difficult problem. And it's both crucial and urgent that we act on this, but fortunately there's also hope, and there's a lot of things going on, not only here, but all across the wind industry and in academia. There's a lot of attention on this. And I think together, hopefully we can solve this challenge to the benefit of all of us. So just to sort of frame it, and I guess most of you already know quite a bit about wind turbines, but the challenge is that these turbine blades, 3 of them make up the rotor. They spin and spin and spin and produce a lot of green energy for all of us. But for them to perform, they need to be huge, they need to be very lightweight, and they need to be extremely durable. They are put up on the most harsh places around the globe. And we have spent decades increasing the performance of these structures. So now they perform really well. They are extremely durable. But the flip side to all of this, and this quite really well performing structures, are that they are also extremely difficult to handle at the end of life. And just to speak into the amount of this problem, here's a graph showing what goes on for land-based wind turbines. So the first turbines put up, they are starting to become decommissioned now, and the numbers are just growing. We're all over, especially Europe. We have a lot of wind put up, and some of them we can extend, but some of these need to be decommissioned and handled in some sort of a practical way. Offshore, they lag a little. There's sort of a little extra lag time there because it started roughly 20 years ago, but around 2030 we will have a lot of composite and end-of-life blades also from offshore wind that we will need to handle in some way. And as Steve just mentioned, these numbers will double and even quadruple really rapidly. So this is a trend that we will see more and more, and this obviously also asks for a way to handle all these materials. And I'll just show you this. This is sort of the hierarchy of waste. So it's every time we have used a resource and are done using it, we as a consumer, but also as an industry, will need to consider what to do with it. And the more value you can retain in that end-of-life product, the better, basically, the better for the climate, often also the better for your wallet, and there have become more and more focus on this. So as I said, one of the key qualities of the wind turbine blades are that they need to be extremely durable. And this also means that it's very, very difficult end of life to do anything meaningful where we basically just split them apart and grab the value that is retained in the material. What is most often used is the elephant graveyard you just showed before, where turbine blades are basically buried. And this is, of course, not a great way of extracting the value that is, of course, in the raw materials that we put in blades. There are a lot of different technologies emerging and a lot of different tries to sort of climb this ladder. Of course, also the best thing you could do is just always just leave it running, never taking it apart. And this is, of course, what we have been doing until now. We've extended the lifetime on wind turbines to several decades. But that doesn't mean that there will not be an end of life. So this is where we are now, and we're trying to address the possibilities climbing up this ladder, basically. And what's on the market now, they are, as I said, they are evolving, they are retaining more and more of the value. But what is really challenging, and what we need to work on, is that these things, they must be sustainable on all different parameters, both financially, also in the energy use. This is a big problem now, that we cannot use a lot more energy in recovering material compared to virgin material. So we sort of need to beat that. We also need to think in transportation. So if we end up with one place in the world where we can recycle wind turbine blades, that we will end up with a lot of transportation issues to have this functioning. So the challenges, that the technical solutions we're having, it's sort of on a multi-sided problem. So it's not easy, but fortunately things are emerging, and that's great. But with composites like this, there's sort of another challenge, is that it's very difficult both to retain some value from the fiber part and from the resin part. So it's usually two different types of expertise that works on these technologies. It's often different recycling routes will benefit either one or the other. And to have a fully sustainable system, we need to think in a very sort of holistic way that thinks in all of this, both the value of fibers, the value of the resin, the energy use, transportation, as I said, and also remaining a financial value. So this is where we find ourselves in the CeTeC project. These are the partners, and it's a relatively small, robust team. We've been working together before, and together we cover sort of the entire tech chain involved in this. So all the way from the university, where we have some of our partners there with a very high expertise in catalytic processes, to the Technological Institute here in Denmark that are experts in bridging between the research going on in university and industries, only in epoxy, that are epoxy producers and sort of specialized in also upscaling this process. And then us making sure that the entire value chain is sort of integrated into the process. But to dig a little bit into the sort of more technical things of the CeTeC project. So the CeTeC project is a project that are trying to address this challenge that the composite resource that we have today is not really seen as a resource, it's seen as a waste problem. And what we have analyzed is that a lot of that could change if you can efficiently take the composite and divide it into a fiber fraction and a resin fraction, and handle those waste streams separately, and hopefully turn them into not a waste stream, but a resource stream. And we already did a lot of this work in the predecessor agreement, where we demonstrated that by making a small adjustment to the epoxy formula, we can basically dissolve it at the end of life. And that also means that we can dissolve the entire composite structure and then handle the resin part and the fiber part separately. And this is the result. You can see that this is this is acetic acid, and a chemical modification. This is the Dreaming project, and so the previous project. And what you can see is that let me see if I can run it again. It swells and dissolves, and this is of course great because this gives us access to work with these. It was also successfully scaled and gave us something to work on further, because the real challenge is maybe not that, wait, okay, I missed something here. But the real challenge is that it's not enough just to take these apart and do this sort of very physical separation. We also need a chemical step where we do a chemical transformation of the epoxy, so that it's not only epoxy dissolved in some liquid, but really going back to the basic chemicals. So that means sort of a new slight adjustment to the epoxy, but more importantly, a chem cycling step. This is what we call it, chem cycling step, that cuts up epoxy chains into base chemicals. And doing that will give us a new raw material that can enter into the production on completely equal terms to the virgin material, and thereby displace the otherwise hydrocarbon-based base components that we use for epoxies. So this is a sort of a potential way of closing the carbon cycle. Basically, each carbon molecule or carbon atom that goes into windmill can go through this process and hopefully enter into a new blade. The focus in this project is solely on the resin, and this means, of course, it doesn't mean that we don't think in the fibers. So it's still important that we are developing a process that retains the quality of the fibers, but hopefully there will be a lot of other clever people that will work on this simultaneously, so we can sort of concentrate on the epoxy side, and then these will meet at some point. Power. So just to sum up what we are doing in the CeTeC project, the project is really young. We are only 3 months in, but we have already seen some quite interesting results, and we already in this sort of quite well-working consortium that has been working together before. And what we are aiming to do is really to do this fully circular step in the epoxy system. And to us investors, it's really important to reach that gap, because when we do the analysis on our wind turbines, we can see that this is where we have the largest gap, right? Almost every other component in a wind turbine is today recycled. It's highly important, and it's also part of our business case. But the blades are still lagging behind. But if we can succeed in transforming this, the composite parts, so especially the blades, if we can succeed in transforming that from being a waste to a new resource, we can really bump us these numbers. We can really start to aim for that 100% circularity, where every bit that goes into a wind turbine or any other large composite structure, composite goes anywhere. If that can be recycled, I think we can move very, very far in this process. And I think with that, I ended up my time, but I'm really looking forward today. I'm really looking forward to suck in all these interesting new technologies that I saw on the agenda. And yeah, we are always happy to hear from clever people with good ideas. So with that, I think I'll leave it back to you, Paul.
Thanks, Mie. That's a fantastic presentation, great overview and understanding of what you're doing there in Vestas. That's a great start. Delegates, don't be shy. Do put your questions in the Q&A at the bottom. With that, I'll ask Harald Stecher to share his screen and give a brief introduction. Thank you, Mie. So Harald Stecher is from Siemens Gamesa Renewable Energy Offshore Division. He's working in wind blades and sustainability, which is central to this seminar. My perspective is it's fantastic that we have specialists within the OEMs actually working on this specific topic, so it's great. He's a materials engineer, master's in organic chemistry. We'll focus on biocatalysts from Graz University. And he's been with Siemens Gamesa for 5 years, I think, Harald. And he's working on future resins and more sustainable materials. With that, Harald, I'll pass the floor to you and let you begin. Thank you.
So thank you very much for the kind introduction and as well also giving me the chance to present here today. So I'll first start with something personal. That's, well, I started CeTeC projects presenting right before me. My resins background taken aside, I decided to maybe give you a view on something else. So some key figures on Siemens Gamesa Renewable Energy. We've also quite a lot of turbines installed worldwide, 26,000 employees. Some solid numbers also on the commercial side. We have a true global and modern scalable footprint and advanced digital capabilities, and we have a portfolio that covers onshore, offshore, and service as well. And I am from the offshore part of the organization, so also my presentation will be focused on offshore blades and turbines. And to give you an idea of the development of offshore wind turbines in general over the last decades, you can see the milestones in offshore wind and a comparison between the first offshore turbines that were installed in 1991 on the Vindeby side in Denmark. So the turbines had a rotor diameter of 35 meters and a power rating of 450 kilowatt. And current flagship model of Siemens Gamesa, the SG14 222 direct drive, has a rotor diameter of 222 meters and a power rating of 14 megawatt. So this means a single turbine now has almost 3 times the capacity of the whole Vindeby site that was the first project. So now after the introduction, it's time to start with the actual topic of sustainability. So let's first have a look on, is wind energy actually sustainable? Wind energy is a sustainable business. Renewable energy sources are also called renewables, so energy sources that replenish or renew themselves naturally. Anything renewable can be replaced or has an endless supply. And typical examples are solar energy, wind, and biomass. And what is sustainable energy? It is a provision of energy such that it meets the needs of the present without compromising the ability of the future generations to meet their needs. So by definition, renewable energy sources are also sustainable energy sources. But taking a closer look at how the energy conversion is achieved, is the energy consumption to produce and manage this energy conversion taken into account? Is waste handling over the whole life cycle of this energy conversion accounted for? And is the environmental impact induced by creating the energy conversion considered? And all this can be answered by the use of a life cycle assessment and its tools to measure sustainability performance of the products. So Siemens Gamesa Renewable Energy has performed a life cycle assessment of an offshore wind power plant employing the 8 megawatt turbines. The LCA evaluated the inputs, outputs, and potential environmental impacts that occur throughout the wind power plant life cycle. This environmental product declaration that was done for this specific turbine is based on full-scale LCA of an average European offshore wind power plant with 80 turbines installed. It includes wind turbine components such as nacelle, rotor, and tower, as well as the foundation, cables, and grid, and also substations. And so to explain a bit on the turbine, the 8 megawatt turbine is the current workhorse of the offshore direct drive platform. The functional unit for this LCA is defined as 1 kilowatt hour of electricity delivered to the grid. So we have identified average wind speed to the turbine IEC classification, being 10 meters per second of wind speed for this specific turbine. And just to also mention it, each wind power plant has a specific site constraints that influence the choice of turbine, tower height, foundation size, and further factors of the infrastructure. So the whole LCA encompasses raw material extraction, materials processing, manufacturing, installation, operation, and maintenance, as well as dismantling at end of life. And the results are presented here. And it also means, when looking at the numbers, that in its entire life cycle, a wind power plant produces, this wind power plant produces 68 million megawatt hours. So it means it's 41 times more energy that it actually consumes to be set up. The energy payback time equals 7.4 months. So this is the length of time the wind power plant must operate in order to produce as much energy as it will consume during its complete life cycle. And how much CO2 can it actually save compared to a fossil power plant? So with a wind power plant taking emissions 6 grams per kilowatt hour, it saves 58 million tons of CO2, and it equals the amount of CO2 absorbed by a forest with an area of 1,667 square kilometers over 25 years. So on this slide, the contribution of different components and materials are shown. Each component and material group contributes to the total CO2 equivalent emissions of the power plant. And among the components, the turbine's tower and foundation contribute to more than 50%, followed by connecting cables, blades, and nacelle. In terms of material group contribution, it's actually steel that has the highest impact on global warming, followed by aluminium and epoxy. In the category with other materials, that consists of minerals, various plastics, chemicals, and wood. Carbon fiber is not shown in this diagram, and this has also a simple reason, because the B81 blade is manufactured without the use of carbon fiber. And here you can see the CO2 contributions throughout the turbine life cycle stages. So the life cycle has been divided into 5 main stages, saying materials, manufacturing of the main parts, installation, operation and maintenance, and dismantling, recycling, disposal at end of life. Relevant transportation activities and energy consumption were included in each life cycle stage. The main contributor to global warming is the material stage with 71%, because of the emissions during materials extraction. The emissions related to manufacturing are minimal with only 6%, while those from installation and operation constitute approximately 1/4 of the total CO2 impact. Due to a high recyclability rate of the turbine materials in general, there is an offset to the emissions at the end of life. But saying this, it is not the case for blades. So far, the presentation has been on the whole turbine or even project level, but now a closer look at the different stages of a blade's life cycle. The first 2 steps in the life cycle of a blade are materials and manufacturing. We identified the types and quantities of materials and energy that had to be extracted and consumed to produce the blades. For the manufacturing parts, we collected data from our own production sites and from our main suppliers. Consumption data for manufacturing, as well as waste and subsequent treatment, is also based primarily on annual manufacturing data from European production sites. And transport of materials to the manufacturing site is also included in the data. A closer view on materials in a blade or in the production of blades. The most important materials in a blade are reinforcements, which are glass and carbon-based, resin, core materials, coatings, and leading-edge protection and adhesives. In production, also a variety of ancillary materials are used, for example, vacuum bags, flow mesh sealant tapes, and more. And on the right, you can see some pictures from the production of blades in the Aalborg plant, with the layout of the glass, closing of the mold, and at last also the infused and cured green blade. And you can see that manufacturing of blades still requires a lot of manual work and experienced, precise workers to achieve the high quality of our integral blades. To get a better idea of the CO2 contribution of the different materials, here a comparison of normalized global warming contribution of different materials. It is clear that carbon fiber has by far the biggest impact of all the materials shown. So it is also the material that requires further research and development to bring down the CO2 footprint. Epoxy has a much smaller CO2 footprint than carbon, but still a bigger one than fiberglass. On the other hand, balsa wood, which is not shown here, can even have a negative CO2 emission because it binds CO2 during growth, and it can bind more CO2 than what is emitted during harvesting, transport, and machining. Now a closer look on composites manufacture with the first example of a glass fiber-based composite. The different material streams and production steps are depicted here. So starting from glass raw materials, which are molten, the fibers are drawn and sizing is applied. Then the fibers are processed to rovings and glass mats and combined with resin in one way or another to form the final composite structure. In the case of wind blades, it's usually vacuum infusion as the dominating process. For each material stream, the most critical raw material process steps can be identified and actions can be defined and taken. In this case, it makes sense to take a deeper look at the resins, raw materials, and manufacturing steps, as well as the glass melting process, avoidance of rare earth additives, and aging-resistant sizing to extend the shelf life of the glass fabrics. And the same for the carbon fiber composites. Main flow diagram is the same, but the steps for the carbon fiber manufacture are shown. So precursor monomers are polymerized to form precursor fibers, which then undergo an oxidation and carbonization process. And at last, the sizing is applied and the fibers are further processed to roving and mats. To save on CO2 emissions, the same actions as before can be taken for the resins, so carbon fiber. The most energy demanding step is the oxidation and carbonization for the precursor fibers, where there's still an enormous potential to find faster and greener processes replacing the current ones. But also raw material stream and nature of precursor fibers offers big potential to introduce cleaner alternatives like precursor fibers from new renewable sources. And waste is another important topic. So waste can be generally classified into three categories. It's manufacturing waste, so where the major production process wastes are resin residues in flow mesh and container, cute resin, composite cutoffs from the blade edges and the root, dry fiber cutoffs, and the grinding from dust, grinding dust from polishing and repair processes. The same for service waste, which is waste that is created during service, maintenance, and repair. And for sure, most important in this discussion also end-of-life waste, so the waste of retired blades, which mainly comprise composite materials. So in the next phase of the turbine lifetime is installation as well as operation and maintenance. So here the components, auxiliary resources, and workers need to be transported to the site. On-site installation also includes the preparation of the site, erection of the turbines, connecting of the turbines to the grid. And for the operation, it's a structural design lifetime of 25 years for the kind of turbines shown here. And it's also actual data that has been collected for this LCA. And then coming to the end of life, it's all about dismantling and the end of life treatment of these turbines. At the wind power plant's end of life, the components are disassembled, materials transported and treated according to different waste handling methods. And in the case of blades, this is most critically actually. And there are some further aspects in the LCA that also need to be covered. That's for planning a new wind power plant. It also includes environmental impact of the installation and operation to minimize negative impacts on birds, marine wildlife, and visual impacts as well. So as stated before, end of life is an important aspect, especially for blades, where for the moment, not many options are available. It's landfill, crushing and using it as filler for cement kilns and using the glass fibers as reinforcements there, but also reusing components in architecture. But unfortunately, the architecture is not able to receive all the blades that will be decommissioned in the coming years. So recycling, meaning separation of fibers and the matrix and reuse of these components is important. So what can be done to reduce the CO2 footprint of a project? Increasing the rotor size increases the annual energy production and so gives CO2 savings. carbon and can help to reduce the overall mass of a blade to allow for longer blades with the same root size. So you have a positive effect of the carbon in the blade, and that easily compensates for the massive CO2 footprint of carbon as raw material. Second factor is lifetime extension. Lifetime can be extended on the existing fleet with direct impact on additional CO2 savings. And also future blades with better health monitoring will be important to estimate the actual conditions and predict the residual lifetime of each blade. And then it's also important to look into waste streams and materials as the third pillar. So at the end of my presentation, I want to show a study based on LCA presented here that has been introduced. So the idea is to estimate the positive effect of the application of a recyclable matrix. So basic assumption is that a resin is used that offers the same properties, but does not need adjustments in the process and can be recycled under mild conditions. Fiber properties are decreased by 10%, and after the recycling, the matrix can be reused for less demanding applications, e.g. as a replacement for polyamide or polycarbonate. So based on these assumptions, the application of such a recyclable resin can lower the lifetime CO2 emissions of a blade by not less than 28%. So this also shows how materials are important to reduce the general CO2 footprint of blades, and a matrix is a key to a more sustainable blade. This also brings me to the end of my presentation. So summing it quickly up, blades become longer to increase the energy output and reduce cost, but also at the same time reduce CO2 emissions. Sustainability generally is a very important factor for us, including both circularity and CO2 footprint. For blades, the driving factor for carbon footprint reduction is weight or length respectively in lifetime, and blade recyclability and material circularity are important for waste and end-of-life management and have a positive impact on the CO2 footprint. Thank you very much.
Thanks, Harald. That's brilliant. It's really great to see some hard numbers put to the case for sustainability. So thank you for sharing that. I note there's a few questions in the Q&A for our speakers in this session so far. So please, speakers, can you look at those and address the ones that you feel most appropriate to? Otherwise, we're going to have a break for 3 minutes, and we'll come back in at 25 to 2 local time, and we'll have our first technical session. So see you in 3 minutes. Bye-bye. Welcome back, everybody, from that short but welcome break. Delighted to chair the first technical session. And our first speaker is Professor Steve Eichhorn, who's a friend and colleague of mine at Bristol Composites Institute. The topic of his talk will be From Micro to Nano and Back Again, Natural Cellulosic Fibre Composites. Now, Steve is really well known for his work in natural materials, particularly with cellulose, and he's won a number of awards for his research contributions over the years. The most recent of which is the Swinburne Medal and Prize from the Institute of Materials, Mining, and I've forgotten what the third M is, but thank you. Yeah, last year, and he's chair of the American Chemical Society's Cellulose and Renewable Materials Division. Most recently, been awarded a national fellowship from our national funding body in the UK, the EPSRC, which is an EDI fellowship, which is a Quality, Diversity, Inclusivity Fellowship on bio-based composites. With that, Steve, the floor is yours, and please take it away and share your screen.
Thank you very much, Paul. Thank you very much. It's a great pleasure for me to be here to give this presentation to you. And I've enjoyed listening to the industry perspective talks. So I'm going to be talking about some of our research, which hasn't really been focused towards wind turbine blades, but I have noticed in recent years that we're starting to sort of get some of this stuff out of the cupboard again and doing something a bit more relevant to your industry. But if I can just sort of start by giving a background and history to natural fibres and where they sit in terms of composites. Nothing's new under the sun, and a lot of this work's been done for, you could argue, thousands of years. But in more recent history, I guess we all sort of turn to perhaps people like De Bruyne, who was a fellow at the University of Cambridge, and helped develop this material called Gordon aerolite, which we used during the war in Spitfires, a natural fibre composite, and it had some really quite sort of impressive mechanical properties in terms of the stiffness and strength, and with respect to the weight of the material as well. So here's some impressive materials here compared to other materials, and this was really done at a time when we were lacking the supply chains during the war to using oil-based materials, so they were turning more to, and things like glass were in short supply. So we're turning to things like natural fibres for that reason. In a similar sense, Henry Ford developed what's thought to be the first industrial natural fibre composite, the hemp soybean oil composite. Here's a picture of Henry Ford taking a hammer to the back boot panel, which is made from this hemp soybean composite. Actually, it wasn't Ford that developed it. It's often forgotten in the history that it was actually George Washington Carver, who was actually born into slavery, and he was asked, he was even begged, for a letter in the record showing Henry Ford begging him to come to the laboratories to help him develop this soybean-based fibre composite. It's not actually clear whether Carver developed the resin or whether he was developing fibres, but he certainly had a big hand to play in the history of this, and is often forgotten. The Trabant vehicle, which was used widely in Eastern Europe, particularly in East Germany, it had a steel monocoque design, but most parts of the body were made from a material called Duraplast, which was a plastic reinforced with cotton and wool. And it's a very lightweight car and excellent fuel efficiency for those reasons. And of course, we have later models of cars using flax reinforced panels, particularly the Mercedes A200, but there are other examples of that too. I will talk about wind turbine blades in a short while, but I just wanted to sort of focus there on the development of automotive, because it's obviously made quite big inroads into that sector, and I think there might be quite a lot to learn from that sector in terms of how it's developed. So why would we want to use natural fibres? Well, plants sequester carbon dioxide from the Earth's atmosphere. It's carbon capture in order to grow their material. So, and in fact, they're a net negative carbon material. If you can use that material then in an application and effectively bury that carbon into an application for a significant amount of time, it can make a big contribution to carbon capture. They're an abundant biomass source. For instance, we only use a small fraction of the boreal forest for industrial products at the moment. They have competitive mechanical properties, compared to things like glass and conventional materials, and they have a much lower density to most synthetic fibres. They have nice qualities in terms of texture and touch, and also aesthetically they look quite good. They also have other interesting properties, particularly in the automotive industry. It became clear that they had really great acoustic damping properties, and so that makes them very useful in certain applications. But one of the biggest things is that they're actually a mature technology. I mean, plant fibres were used quite extensively through the ages, and just get my laser pointer up here. And here's an image of an old textiles factory here. And in terms of being able to weave materials and process the fibres, it's quite a mature field. So where can we get natural fibres from? Well, they come from all over the world. We have cotton, flax, jute. Here's some nanomaterials that we've been looking at. This is actually the only known animal that produces cellulose. Tunicate, which is a sea squirt, hemp, kenaf, nettle, we've got rami. I always like this one here, Eichhornia crassipes, named after me. So it's actually a pest in a lot of African countries.
Steve, it's Paul. Just sorry for interrupting you, but we're getting intermittent sound issues. I'm not sure if there's anything you can do from your end, but just to make you aware of it.
Yes, I'm very sorry about that. People do complain about that. I'll just try and change the microphone settings, see if that's any better.
It's not a major problem, but just thought you should know. Thanks, Steve.
Oh, thank you very much. So moving on, we have properties of natural fibres, and I don't want to say too much about this because actually one of our speakers later on in the session is going to say probably quite a lot about these diagrams. But these are Ashby diagrams, tensile strength versus Young's modulus for natural materials and engineering materials. And the only thing that I really wanted to sort of point out is that some of our fibres that we're talking about here really sit up in the same regions as some conventional materials like glass and so on. So actually, if we want to make a drop-in replacement, it's from this perspective, it's quite clear that we could do that quite easily. But one of the bigger issues though with natural fibres is, of course, the variability of properties, and of course you can get huge ranges of properties even within one species, but also between different types of materials. So all of these fibres here have very, very different properties. And depending on what material you pick, you can also get the range of properties as well that they give. And sometimes from an industrial perspective, that's not really very desirable. Just to sort of move to wind turbine blades, I mean, natural fibres have been used before in blades. We're aware of wooden blades, but actually it was the Chinese who developed this design for a wind turbine to pump water, and this has been known about for 2000 AD. You know, wind-powered turbine pumps were being used in China, Persia, and the Middle East, and they used woven reeds, and actually later they used woods in those designs. And of course, a lot of our blade technologies are designed on Dutch blades, but actually I see that the designs are coming forward based on these old Chinese designs. Here's a picture of a reconstructed Chinese wind turbine blade system pumping water using this Archimedes screw. Now, we've been working on natural fibres for some time. I only put these two slides up that I'm going to present just to sort of point out that we did quite a lot of work in the early days in trying to map stresses, or be able to use a technique called Raman spectroscopy to map the local stress state inside natural fibres. And I bring this up because actually I see some of this work might be useful for doing in situ mapping of blade materials possibly. But here we're able to measure what's called a Raman shift. So we take a fibre and we deform it in tension, and then we measure the position of a particular band in that spectrum, which corresponds to a stretching of the cellulose chains, and then we're able to do point-by-point mapping along the fibre once it's inside a composite, and that gives us the in situ stress state without actually having to take the composite apart. We can actually do it in situ. And we did this with a number of natural fibres. This is perhaps one of the sort of better techniques that we can develop here, where we have a glass fibre and a natural fibre close to each other, and we're able to see a defect in the glass fibre actually interacts with and generates a stress concentration of natural fibre. So we're able to do sort of local mapping of how fibres interact with each other. So if you had a hybrid system where your fibres were in close proximity, then you could have a look at both the glass and the natural fibres there together. And we used a little dopant inside the glass fibres, so we were able to make some glass fibres using samarium fluoride and samarium oxide, which are luminescent, and then we're able to then map across the defects in the composite structure. But on to some more recent work that we've been doing, and Ali Kandemir, pictured here, is the sort of brains behind this, and we've been looking at natural fibres, a whole range of different natural fibres, with the view of using short and discontinuous fibres in recycled, if you like, composites, or composites that could easily be made into sort of flexible parts and so on. And he's been looking at all sorts of different fibers, jute, kenaf, coir, and flax. And he's been measuring the interfacial properties using the this setup here, where you pull a fiber between two blades and you measure the force required to pull the fiber out from a microdroplet of resin. And he's been calculating some critical lengths. Now, just a quick take-home message, this fiber here, the coir fiber, is actually the best fiber, it would seem. It has a reasonable critical length associated with it, but it also has reasonable mechanical properties. And we found that these fibers plus flax were probably the best in terms of their overall performance. And then he's moved on to looking at some short natural fiber composites using, and I'm sure Ian Hamerton's going to talk about this later on. And so I won't go into too much detail about this, but this is a hyperdiff method where we take short fibers and make these continuous composite tapes using them, and the properties of these composite tapes are really quite impressive. And he's been able to take all of these fibers and also mix them with different resins as well, so epoxy, PLA, and polypropylene here. We found that PLA is a pretty poor resin, but flax and coir have got the best properties in terms of their use in the composites that we've been using. And so we're moving on now to look at other composite systems and trying to sort of get a better understanding of how the natural fibers can compete or maybe even combine with glass and or carbon fibers as well. We've been spinning our own fibers as well. So sometimes you need a long fiber, but that's not always possible with natural fibers. They have very limited lengths. So we've been making fibers, spinning them in a novel ionic liquid solution. Ionic liquids are interesting because they're a so-called green solvent. They're much better for the environment than things like viscose. And so we've been making fibers using this ionic liquid 1-ethyl methylamidazolium diethyl phosphate. And we've also been combining some of the solvents with other solvents to get mixed solvent systems. And we've been able to make some pretty reasonable fibers with decent enough properties. And they've got potential to replace glass. And Chen Zhu was working on this. She's now at Imperial College doing some further work on protein fibers. But this work was really quite good in that sense. We were able to make fibers using DMSO as a co-solvent, and we were able to get some really impressive properties. Stiffnesses of about over 40 gigapascals and a strength of just over half a gigapascal. And these fibers really are, at the top end of what we call regenerated cellulose fibers, and they could be really useful for making proper structural composites. We were also able to spin fibers from waste. So Cynthia Adu, who was at Cranfield University, supervised an NGD project of hers, and she was taking some of these paper mill sludge materials. So in a paper making process, you end up with a lot of waste material, and the sludge material is typically just thrown away or burnt. And so she was looking at trying to make materials from it, and we were able to make some sludge fibers. And here we can see on an Ashby diagram, the sludge fibers are pretty good compared to viscose, certainly. So we were able to make some pretty decent fibers from what is essentially a waste material. Now, I'm not going to dwell too much on nano, but we do quite a lot of work on making nanomaterials of all different types. And the concept is if you take a tree here, it is actually a hierarchically structured material. You have the trunk of the tree, and the tree has these ring structures here, and the rings are made up of these fibers here, which in turn also have a layered structure. And within that layered structure, you've got these fibrils, and then ultimately you've got the molecular chains of the cellulose. You've got hemicelluloses as well, these sort of twisted and bent molecular chains here. And then pulling all this together, you've got the lignin essentially. But you can extract the fibrils from these materials. Here's some fibrils here from cellulose, but you can also extract these nanocrystals as well by using chemical treatments. So you can get different architectures of cellulose from different materials. In fact, this is the tunicate here, and they produce some really rigid and stiff materials. Now, we've been looking at all kinds of different composites, and I wanted to just bring to your attention this particular system here that's being looked at by one of my new PhD students, Guofran Zhu, and he's been making some cellulose nanocrystals. So here we take the plant material, which has crystalline ordered regions and amorphous or disordered regions within it, and we take a strong acid, and this hydrolyzes the amorphous regions more readily than the crystalline regions. So you end up with these rod-like cellulose materials, which if you do this using sulfuric acid, you get a negative charge on the surface. So these things are dispersible in water, which is quite useful for green processing. Now, we've also been able to add some octyl groups. So this is a carbon chain on the surface. So this is a hydrophobic group. We've been able to do it where we also retain the charge. So what we end up with is effectively a surfactant-like material, a bit like soap. Now, we know soap forms what we call micelles in water, where these fatty chains, these hydrophobic groups, point towards the dirt. They encapsulate the dirt, and the charge points towards the water. So you can actually encapsulate dirt, and that's how soap works. It sort of washes the dirt off your hands. But you could do this in a composite as well, and we do this using what's called a Pickering emulsion, which is this is an emulsion here, but this is a Pickering emulsion where we use a solid phase for the emulsifying. So we use these octyl CNCs, and they'll sit at the oil-water interface. But we can encapsulate all kinds of oils in here. We can use water-based polymers in here. You can do the reverse, where you have a water in oil emulsion, but this enables us to make these capsules here, and the cellulose nanocrystals sit at the surface here. And we've been able to make just very recently some self-healing composites where we encapsulate an oil that, when it comes out of here and reacts with the air, it forms a healed system. And of course, the nanocrystals as well act as a reinforcement in the composite. And so there's potential to make self-healing composites using green systems.
Steve, sorry for my rudeness, but we are running over now. So if you could bring it to a conclusion.
I'll bring it to an end. This is my last slide, very last slide. So we've been looking most recently, going back to wood and looking at wood itself, because wood is a hierarchical structure. It has a nanostructure. We've been compressing it and in simulation here, but working with a group in Maryland, they've been able to make large pieces of wood that have really high mechanical properties. So here's an attribute diagram here. These are some typical woods here. So we can get a very, very high modulus of elasticity. It's a higher density than these bits of wood here, but certainly exceeding anything that's been seen in the nickel so far. And they're also able to make it transparent. So I wrote a little article here in the conversation about making transparent. And that's the end of my talk.
That's great, Steve. A fantastic history I was learning about from the early development composites, but actually what you were showing at the end is how real these natural materials can be for full-scale structures. I notice there's questions coming in the Q&A, which I think might be suited for you. So take a look at those and respond as you see fit. But with that, I thank you again, Steve, and we'll pass over to our next speaker, who's also a colleague and a friend, this time from the Burnell Institute at University of Limerick. It's Dr. Maurice Collins, who's a senior lecturer there with specialism in biomaterials. He's also the editor of the International Journal of Biological Macromolecules. And with that, Maurice, the floor is yours. Please go ahead. Thank you.
Okay, I'll just see if I can get this is the hardest part, getting my presentation.
Yeah, you just go into slideshow mode.
Yeah, so we're okay, I think.
it looks great. Thank you.
Okay, thanks, Paul. Thanks for that nice introduction. So I'm going to talk today about lignin. So lignin fibers and lignin carbon fibers. So carbon fibers based on lignin. So this is my first slide here is just so those of you that may not know where Limerick is. Limerick's on the west coast. It's on the west coast of Ireland, so 200 kilometers southwest of Dublin. And that's a photograph of our campus. And we have the River Shannon running through it. And as you can see, it's quite green. There's a lot of cellulose, a lot of lignocellulose, a lot of lignin. So a lot of potential for renewable materials. So just a little bit of background. The current situation is that all composite materials that we use in wind turbine blades are fossil-based. Thermosets, thermoplastics, the carbon fiber that they're reinforced with. So these materials, they come from petroleum. They're polluting, bad for the environment, large carbon emissions. Then there's other carbon materials like graphite that's mined out of the ground in places like China. And these are bad for the planet as well, but not only bad for the planet, they're also bad for human health. So we're currently in a difficult position when it comes to our materials. So just to bring it down here to the bottom left-hand side of the slide, and this is a kind of a chronology of materials development. So starting all the way back in the Stone Age, up to more modern times, where we're looking at composites in the 1980s and 2000s. That was the composites age, and now we're coming towards the intelligent materials, and low carbon materials age. And we need to do this because if we don't, we're likely to have a very bleak future. So we need to have some low carbon materials, sustainable materials to take us to the future for future development. So you remember the first slide I showed you of our campus here in Limerick. So we have a lot of trees, but the idea is that we don't cut down all those trees. What we do is we use waste. So this is the waste materials currently used in Europe. These are accumulations of waste. And from these waste materials, you can derive biomolecules that I've listed here on the right-hand side. And one of the biomolecules that we're interested in is lignin. And that's what we use for producing carbon fiber. And there's tons of this available each year as waste. So I coordinated a H2020 project called the Libre project, and that was about producing carbon fiber for composites from lignin, so a fully bio-based carbon fiber. And the idea behind it was that we're moving from this linear process where trees are used to produce cellulose, and the cellulose is used to make paper, and that a byproduct of that paper making process is lignin. And that byproduct is, as I said, 98% waste and 2% is used as a low value energy product. So what we do is we take that waste lignin, and we blend it with other biopolymers using over 50% lignin. So this is the unique part. We use over 50% lignin. We blend it with other biopolymers, and we produce a precursor fiber. Uniquely as well is that we scaled this fiber to TRL 4 or 5. And then we converted this precursor fiber to carbon fiber, and we converted it using conventional processes, which involves using conventional ovens, furnaces, where you heat the precursor to 1,000 degrees C and it gets carbonized. And we also converted it using a low energy microwave technology, which I'll talk to you about in a couple of minutes. So that carbon fiber then was put into a polymer matrix, and it produced a composite material. And those composites were then used to make demonstrator parts. So the reason that we were doing this, the drivers were that it's a move away from petroleum-based materials, increased sustainability, reductions in energy consumption, greenhouse gas emissions. We were using a non-solvent processing technique, so we were spinning these fibers, but we didn't spin them using solvents. We spun them using a melt spinning, so we took solvents out of it. Conventional carbon fibers are made from fossil-based pan materials, and they're spun using solvents. As well as being fossil-based, they also use solvents, and they also use extremely high temperatures. So that's why you might remember one of the earlier presentations, it was showing that there's a huge carbon emissions associated with carbon fiber production, and that's why. So another driver was cost reduction. So we wanted to reduce the costs. So we were looking at costs of about 5 to 7 euros per kilo. Mechanical properties is always something that's extremely important when it comes to carbon fibers. And our targets were 2 to 3 gigapascals and 200 gigapascal modulus. Now you remember from the previous presentation by Steve that the high end for natural fibers is about 0.5 gigapascal tensile strength, and a modulus is about 40 gigapascal. So you can see that these targets are way higher than typical natural fiber mechanical properties. Carbon yield, about 35% we were looking at, greater than 35%, and we actually achieved higher than 50%. So this was the processing route. So we get technical lignin as the waste from the paper making industry, and we purify it and we refine that technical lignin. And then we can modify it. Sometimes we chemically modify it, sometimes we don't. We just use it as is, and then we blend it with another biopolymer. We tried various biopolymers. I'll talk to you about those in a while. We spun those blends into fibers. Then we stabilize them before we convert it to carbon, because you have to stabilize. If you don't, it'll just melt. So we needed to stabilize it. So that involved some nice novel cross-linking regimes that were able to cross-link the fiber as we heated it up. Then we heated it to 1,000 over 1,000 degrees C, carbonized it, did some surface treatment before deploying it in a composite. We use those fibers for structural applications, but we also use them for functional applications. So we did some activation, did some surface treatment, and use them as functional composites as well. And then you can also go the route of graphitization, where you can make graphite fibers. So these were the routes that we followed. And so just to talk about the precursor fibers themselves. So we got 50% or more lignin, and we blended it with all these polymers that you see listed here. These are all bio-based polymers. I X out the ones that didn't work. And what I mean by didn't work is that these polymers were not compatible. They were incompatible with lignin. So you can use Fleury-Huggins technique to be able to predict this. But we did the experiments, we did rheology, and we looked at these on a microscope, and we saw that they were incompatible. There was phase separation. And when you get the phase separation, then when you carbonize, the phase that separates becomes a void. So you end up with carbons that are full of voids, which are not suitable for structural applications, but they are really good for functional applications. So they didn't go to waste. The other materials that are not X'd out, these were compatible with lignin, and that means that when we mixed them, that it was a homogeneous phase, and when we carbonize them, we got a nice carbon phase with no voids. And you can see an example of that here. So this is a precursor fiber here up in the top right hand side, and this is a blend of lignin with thermoplastic polyurethane that has been derived from castor oil. And you can see the cross section using scanning electron microscope, and there's no voids in it. Then we carbonized that precursor fiber, and we produced a carbon fiber with no voids. So that was an excellent result. That was published in Sustainable Chemistry and Engineering not so long ago. Now this is it's one of my favorite slides. It shows the mechanical properties of our fibers. And so if you look at the mechanical properties here, if you see the tensile strength on the y-axis and modulus on the x, and the state of the art is here for carbon fibers. Now, if you remember there, the natural fibers themselves will be down at the bottom left-hand corner, but carbon fibers produced from bioresources would typically be about 100 gigapascal modulus and 1 gigapascal tensile strength. But you can see up here on the top right-hand side, this is the types of mechanical properties we were able to produce. So we got to 2 gigapascal tensile strength and 200 gigapascal modulus. And these are the type of properties that you can deploy in wind turbine blades. And not only that, not only did we produce these types of mechanical properties, we were also able to scale these fibers. And you can see images here. This is the precursor fiber before it's carbonized, and then over here this is the carbonized. So it kind of turns black after you carbonize it. So once we produced the carbon fibers, we then did some surface treatment, and this work was done at my colleague's lab, Dr. Ida, in the Fraunhofer in Bremen, where he did some surface treatment using microwave plasma, dielectric barrier, surface modification, and atmospheric pressure jet plasma. So we did the surface treatments before we deployed them in the composite materials, before we deployed them in matrices. So these are some of the composites that we used. These are some of the first demonstrator parts ever produced using lignin-based carbon fiber. So we produced a continuous fiber. We infused it with some epoxy, and we produced a small turbine blade. You can see here at the top of the screen, and this is a small turbine blade that was produced as a demonstrator. And this was done by our partners. ORE Composites did this. They produced this little blade for us. We also that was produced from continuous carbon fiber. We also produced chopped fiber, so we chopped up our fibers, and we injection molded them with a polyamide, and we produced these carving mirrors here as demonstrators. And so all this was done, and we did some life cycle analysis on this as well, and we produced a 75% energy reduction considering a microwave heating, which I'll talk to you about in a second. And there was a 66% reduction in carbon emissions. So we got these life cycle analysis data based on the fact that we were using fully sustainable carbon fibers, but also the fact that we use a microwave technique to be able to produce these fibers rather than conventional heating. And just a few words on that. This is a disruptive technology that we've developed here at Limerick, where we can produce carbon fibers using a microwave. It works for lignin and for PAN, so it works for traditional carbon fiber as well, the precursors. And if you put a PAN precursor fiber into a microwave and you turn it on, nothing will happen. It doesn't absorb microwave, neither will lignin. So what we did is we put a little coating, a little susceptor coating on the surface of the fibers. So when you turn on the microwave, it then heats up and carbonizes. So we can control this by controlling we're controlling the power on the microwave, and by controlling the power, you can control the heat. And you can see here that we were able to reach temperatures of over 1,000 degrees C. So we're able to produce carbon fiber. Not only that, not only do we produce the carbon fiber and have low carbon emissions associated with it, but we were able to produce the carbon fiber in a matter of seconds. And we did mechanical testing, and we compared the carbon fiber produced using conventional ovens with the carbon fiber that we produced using the microwave, and they retained their mechanical properties after microwave production. So this is something that's this is really something that we really want to take further. So we optimized heating. The first trials we got a lot of porous because we're not optimized heating, but once we started to optimize the heating, we were able to achieve the mechanical property. We were able to achieve fibers without porous, and that's why we were able to get really good mechanical properties. So I'm just going to quickly have a couple of slides. I know Paul is showing his face, so that's a bad sign. But just two more slides, and we also produced some nano composites, and these were produced from the materials that were immiscible with lignin, so they form porous. So we use them for functional applications. So we spun these, but we spun them at a smaller scale. We spun them at the nano scale. So instead of producing fibers for carbon fiber, we produced nanofibers, and then we converted those nanofibers into nano carbon fiber, and they were porous, and we used those in anodes and batteries, and the capacitance was really good. The typical material now for an anode is graphite. It's fossil based, and it has a capacitance of about 300. Our sustainable carbon fibers, nanofibers, were twice that, so they're twice as good. So not only are they sustainable materials, always people talk about sustainable materials and say that their function is a lot less than fossil-based materials, but these materials outperform fossil-based materials as well. So that's the key message. We use the same materials, these porous nanofibers for diabetes treatment. So the idea here was that we produced these nanofibers, we put them on a gold layer, and we were able to detect glucose. So it was a quick detection of glucose. So we use them as a diabetes sensor for glucose. So what's next? We're currently in a new project. It's a new Horizon 2020 project on recycling composite materials. We're looking at epoxies, bio-based epoxies, but not the bio-based epoxies that you get off the shelf, which are about 30% bio-based. These are fully bio-based epoxies. We're recycling these epoxies by using a reversible cross-linking technique. And the key thing here is that bio-epoxies now, any bio-epoxies now, they're based on synthetic cross-linking chemistries, but these ones that we're producing are based on fully bio-based cross-linking technologies, and that they can uncross-link on demand. So you can trigger cross-linking, and it makes recycling a lot easier. And not only that, we obviously combine these bioepoxies with our biocarbon fibers to produce fully bio-based composite materials, and hopefully we'll see them in wind turbine blades. That's all for me.
That's perfect, Maurice. Timing was perfect as well, so no worries there. Just want to invite delegates to put comments in the chat and use the Q&A as necessary. Keep the questions coming. There's been some great discussion and questions and answers already in there, so if you haven't checked it out, please do so. With that, we'll move on to the third speaker in this first technical session, and it's a pleasure to introduce to you Dr. Dimitrios Mamalis, who's from the Offshore Renewable Energy Catapult. He has a bachelor's and master's, so I think Dimitrios is top-ranking university in Greece, National Technical University of Athens, NTUA, and he also holds a PhD from the University of Edinburgh in chemical engineering. And his ongoing research interests are in thermoplastics and thermosets for wind turbine blades, as well as hybrid composite materials. And he's going to discuss alternative hybrid composites, a novel fiber metal laminate based on thermoplastic resin. So with that, Dimitrios, the floor is yours. Please share your screen.
Hello everyone. Just I'm struggling to share my screen. 1 second. Give me 1 second. Sorry for the delay. So, can you see my screen now?
Yeah, that looks perfect. Thank you, Dimitrios.
Hello everyone again. Thanks for the introduction, Paul. Hope you can listen me clear. Today, I will speak about alternative hybrid composites and the concept of a novel fiber metal laminate based on thermoplastic resin. As mentioned from the previous speaker, the wind energy industry has grown consistently the last decade, resulting approximately 591 gigawatts of installed wind capacity worldwide as of 2018. The blades of wind turbines are constructed primarily of composite materials, and with estimates of 9.6 metric tons of composite material per megawatt of installed capacity. With the current used thermoset composite materials, the majority of these blade materials end up in landfills at the end of the blade's life, resulting in an immense amount of composite materials going to waste stream. One alternative option to landfilling is to recycle the blades at the end of their lives. However, with the current thermoset resin technology, recycling is challenging and typically leads to low quality byproducts that are significantly devalued compared to the original materials. And also, the lack of recycling infrastructures make current processes quite expensive. By 2025, the annual composite waste for wind is estimated to be around 66,000 tons. As such, estimations of material stocks and flows can be accurately made. Characteristically, the figure presented on the right side, you can see the age of onshore wind fleet in Europe. As can be seen in the figure, Germany will have to deal with a big amount of old blades in the near future, then Spain, and follow France and UK. In the next slide, the amount of wind turbine blade material expected to reach end of life in the coming years in Germany, Europe, and worldwide from 2020 to 2034 is shown in the figure. It is clear that the amount of blade waste worldwide is increasing rapidly across the years. In turn, the development of low cost and effective recycling material and processes is vital for an environmental point of view. Recently, the development of an infusible thermoplastic resins for composite wind turbine blades showing that recycling has real potential. In addition to the recyclability aspect, thermoplastic resin can be enable longer, lightweight, and lower cost blades. By replacing thermoset resins in wind turbine blades manufacturing processes with thermoplastic resin system, there is a potential for reduction in blade manufacturing cycle times, as well as reduction in the embodied energy. Thermoplastic resin systems can polymerize at room temperature, eliminating the need for heated tooling and ovens for post-cure, resulting in manufacturing equipment cost and manufacturing time reductions. Infusible thermoplastic resins such as helium, developed by Aikima, can be used with existing thermoset manufacturing technologies and methods for wind turbine blades. Helium is a reactive monomeric liquid resin that is polymerized into a solid thermoplastic after infusion. Going now to the actual content of this presentation regarding the fiber metal laminate study. At first, fiber metal laminates are hybrid materials consisting of thin layers of fiber reinforced polymers and metallic sheets. Fiber metal laminates compared to fiber reinforced plastic has advantages such as excellent fatigue and corrosion resistant properties, damage tolerance, impact resistance and strength, flame penetration resistance, and it can be used as lightweight hybrid materials for aerospace, renewable energy, and automotive applications. And now, the advantages of thermoplastic FML fiber metal laminates over conventional thermoset fiber metal laminates are the superior impact resistance, high fracture toughness, extensive fatigue life, the possibility of thermoforming and repair and processing this kind of hybrid composites. Also, there is high recycling potential. Future application of FMLs in offshore structures include the towers of wind, tidal turbine blades. Also can be applied as a leading edge protection material. And also there are other applications of FML can be found in ship construction, including catamarans, high-speed crafts, and boat hulls. Next, I will give you a quick brief overview regarding an EPSRC CAMRENC funded project, namely thermoplastic fiber metal laminates for application in renewable energy that was carried out between Edinburgh University and Offshore Renewable Energy Catapult. You can see also the published work related to this concept, and I can share more technical information if someone is interested, since the duration of this presentation is quite short, so I'm not going to go deep into technical details about this study. So the objectives of this project were to first develop a new generation of low-cost recyclable hybrid fiber metal laminates based on a thermoplastic matrix. Manufacturability of these thermoplastic FMLs by the in situ polymerization route using a vacuum-assisted resin transfer molding technique at room temperature. Third was to establish an acceptable level of bonding between the metal and the thermoplastic matrix. And finally, investigate the mechanical performance of the manufacturing thermoplastic FMLs. You can see here on the right side the schematic drawing of this approach. Next. So, in order to fabricate, very briefly, in order to fabricate these fiber metal laminates, we have used a commercially available unidirectional e-glass fabric, helium 180 grade liquid thermoplastic resin supplied from Aikima, and aluminum alloy 6082 tough 6 is the grade and the form of a sheet 0.71 millimeter thickness. So activation of the surface topography of the aluminum alloy sheets was performed by applying different chemical and physical surface treatments, including alkaline and acid etching, anodizing, and atmospheric plasma treatments. Characterization techniques of these aluminum treated surfaces, activated treated surfaces, was performed using wettability, surface energy, and surface topography measurements. Also, the spectroscopy was acquired in order to investigate the chemical composition of the treated aluminum surfaces in terms of the functional groups. Fabrication of the FMLs was carried out using a hand layup Vartem technique. Holes, flow paths were drilled in the central zone of the aluminum sheets to allow resin to flow across the thickness of the preforms during infusion. And also the FMLs were constructed with a 2-to-1 configuration. Here you can see the design of this whole map of the aluminum sheets used to manufacture these FMLs. And then on the right side, you can see the FML layup after infusion. In this slide, you can see images taken with a 3D microscope of the aluminum treated plates after the application of the different surface treatment using a coherent scanning interferometer. it is clear that its applied method resulted in different topographical characteristics, as well as with a varying surface chemical functionality. In turn, different mechanical and chemical interlocking phenomena are expected between the thermoplastic resin and the metal phase, affecting the bonding strength of the hybrid system. In this slide, you can see some SEM micrographs of the thermoplastic fiber metal laminates, highlighting the good adhesion and bonding and the bonding between the composite and the metal phase of the tested FMLs, as shown in the figures on the right, on the left, on the right side. Also in the center, you can see the fully wetted fibers, pointing out the strong adhesion between the matrix and the glass fiber that was achieved. Here are some concluding remarks from this study. A suitable surface treatment conditions were identified for these aluminum alloys, and in terms of surface roughness and chemical activity. Varte manufacturing of the FML was successfully carried out using helium thermoplastic resin, which are the first of the kind. Flexural interlaminar shear performance of the GFRPs and the FMLs based on helium were examined, and the measured properties were in comparable range with the published literature. Mode 1 interlaminar fracture toughness of the FML was found to be significantly higher, characteristic number of 410 joules per square meter compared to the reported value of 131 joules per square meter of epoxy-based FML in literature, and also with the same configuration, of course. Also, a novel way of bonding aluminum alloy sheets and thermoplastic composite laid through the in situ polymerization technique was found to be successful. Regarding the future work, and some of these tasks have been already been achieved through different publications that we have at the moment. So achieving an optimized metal composite bond strength by a suitable technique which is industrial viable, such as plasma activation. Optimization of the FML manufacturing with a minimum processing defects and deep understanding of the diffusion mechanism. Also manufacturing FML with high consolidation quality and consistency, and generating mechanical property data with a thorough investigation of the damage and failure mechanism of these manufactured FMLs. Also exploring the feasibility of press forming of these FMLs, investigate chemical and water resistance, some investigation around recyclability, weldability, and repairability of these FMLs, and finally evaluating the commercial availability of this technology along with our industrial partners. Thanks for your attention. That was me.
That's great, Dimitrios. Fantastic presentation, and you're getting us back on time. Much appreciated. So, delegates, that concludes the presentations for the first technical session, and now we have opportunity for some live Q&A. So I suggest that if you write down the questions in the Q&A, I'll read them out and I'll pass it to the relevant panelist or presenter. So first of all, I'm not sure this is a loaded question, Crahur, whether you know, but from Crahur Brady at Edinburgh, Dimitrios, how is the ORE Catapult bringing the University of Edinburgh thermoplastic and the FML work to higher TRLs? So that's to you, Dimitrios. If you could unmute, that would be great.
Yeah, thanks for your question, Crahur. Currently, we're working on this concept, trying to, since with Edinburgh University, we managed to see the feasibility of this technology, and we, with some other projects, we try to enhance the bonding capability of the thermoplastic resin with the metal phase. Now we are trying to think at a bigger scale, and as I mentioned, these thermoplastic materials could be used as potentially as a leading edge protection material. Due to these high performance, mechanical properties, but it's something we're working, trying to understand, different processes, and except for vacuum infusion, you can try to use another mechanism in order to manufacture these FMLs with, as I mentioned, with high consistency and high consolidation quality, which is vital for the mechanical performance of these materials. I'm not sure if I completely answered your question, but thanks.
I think you did. I'm just going to say, from my perspective, it's great to see early technology readiness level work at universities being taken forward at the intermediary organisations such as the Catapult. So we all probably, most people in this call have heard the Valley of Death. It's very difficult to advance technology from research level to actual wealth creation. And that's the purpose of the Catapults in the UK. So I'm really pleased personally to see this going forward. There will be a question for Mie and Harald, if Harald is still in the call later, but that's from the industrial session this morning. But if there's time, we'll come back to that. In the meantime, there's been a question directly emailed to me rather than Q&A for Maurice. And it's basically about if there's any issues with the variability or different types of lignin available and whether that affects the ability to carbonize them.
Thanks for the question, Paul. No, is the simple answer. Basically, the most important thing is purity. The lignin needs to be as pure as possible, so there can't be any sulfur or any metal contamination, because if there is, that leads to defects, and that has detrimental effect on the mechanical performance.
Okay, that's very succinctly put. Thanks, Maurice. Great answer. Then we have a question from Agaliki Chantelli for Dimitrios. I'd like to ask if there was a post-curing step added during the manufacture of your samples, Dimitrios.
No.
That's quick.
No, actually, the samples were cured at room temperature, and we didn't follow any post-curing step.
I'm making it simpler anyway, so that's good to hear. There's no more questions in the Q&A. Please get them coming. But in the meantime, if Mie or Harald, maybe Mie first, can respond to Tuan's question. It's quite long. It's referring to industrialization in Vietnam. So I guess Tuan's from there. They use Vestas and SEG WTG components, wind turbine G group gear, I'm not sure. And then the Ministry of Natural Resources Environment has not requested on what we have to do when the blades are retired. What is your plan for blades in Vietnam? I'm not sure if you personally would know the answer to that, Mie, but any insight you have to that question would be much appreciated.
Yeah, no, I don't have any specific knowledge about what they will do in Vietnam. What I know is that, of course, it's a major focus for us to advise our customers on how to handle their blades end of life. It's important to know that we do not own the turbines, we sell them and we service them. And that also means they can last for a long time, but we do not own them. And this also means that we can advise our customers on how to do that, but we cannot really determine. So it's a collaborative, and it's important that all the stakeholders are aware of these end of life challenges that we have. That all the players on this field play together to solve this challenge.
I completely agree with you, Mie, because actually, I mean, the real question is whether there needs to be government action through policy, which enforces developers, the business people, to actually do something in their life. And I think that's an ongoing discussion in Europe. I'm not sure about Vietnam.
Yeah, absolutely. So Wind Europe has now just supported the ban for landfill. And of course, that might be to some little counterintuitive when you see a lot of blades ending up there. But for us, it's really important to sort of push this development and push all the initiatives that going on to solve this. And one driver there could be an official ban or of what not to do, because hopefully that will drive not only the wind industry but all composite industries to handle this challenge.
Yeah, very good points. Yeah, well made. Just seeing if there's any other questions out there. Give it a minute or so. Just looking in the chat. Sometimes people put stuff in the chat. Okay, last opportunity for anyone to ask any questions before we'll have our break. We were meant to convene have a break at 2:30 and then come back at 2:40. So with that, you can keep the Q&A going in the chat. It just won't be answered live until the end of the next technical session. But with that, thanks for your attention. Hope you're enjoying the seminar as much as I have done so far, and I'll be part of the delegates and panelists for the remainder of the seminar. So enjoy your break, and we'll be back at 2:40.
Hello, everyone. Good afternoon, good evening, or good morning, wherever you may be. This is the second installment, if you like, the second session we have for you. We've got 4 speakers this afternoon. My name is Mark Forrest. I'm the Blades Research Lead at the Catapult, and I sit in the Research and Disruptive Innovation Directorate there. We've got a range of speakers this afternoon. Across from industry perspectives as well as design, materials and manufacturing. So without further ado, I'd like to introduce our first speaker of the afternoon, specifically Jenny Banks from the National Composites Centre here in the UK. Jenny is an associate research engineer within the materials and process team at the NCC. She's trained in woven textiles, and her research interests predominantly focus on the development of sustainable composites and novel technology development for end-of-life composite processing. And I understand Jenny will give an introduction to the SUSWIN program, which is delivered in partnership with the ORE Catapult and supported by the Crown Estate and Renewable UK. I believe she'll go into some learnings to date within the SUSWIN Sustainable Materials Workstream, focusing on using LCA to assess the impact of alternative blade materials. So yeah, Jenny, take it away.
Thanks, Mark. Let me just share my screen. Let me know if that is good to go. We good?
All good.
Fabulous. Okay, so hi everyone, my name's Jenny. As Mark said, I'm part of the Materials and Processes team, and I'm quite heavily involved in a programme that we have at the National Composites Centre called SUSWIN. So that's what I'm going to talk to you about today. I'm going to give you a kind of short intro to SUSWIN, so what the ambition is, who's involved, and what our approach is, essentially. And then I'm going to delve a little bit into one of the work streams that's active at the moment within SUSWIN, focused on future sustainable materials. And although we're at quite an early stage in the SUSWIN programme, we don't necessarily have sort of conclusions in the work stream that I'm involved in at this stage. There are some sort of learnings and considerations around approaches to LCA and assessing impact and things like that that I thought would be interesting for you all. So I'm going to share that with you. So, oh, hang on. How do I change slide? There we go. So what is the SUSWIN programme? So for any of you that aren't familiar with SUSWIN, it's an initiative that was launched, I think last November, November 2020. And our vision is really for the wind energy industry to become zero waste across its entire lifetime, its entire life cycle. Now that's no mean feat. Lots of zero waste challenges are being tackled at the moment, and they're typically very complex and multifaceted. So SUSWIN is really focusing on accelerating the development of technologies, processes or materials that address not only sort of the recyclability of existing blades and blades that are about to be decommissioned in large numbers, but also to accelerate the development of materials or processes for future wind blades as well. And the way that we aim to sort of realise that is by, kicking off sort of 3 key work streams, which you can see on the right here. So that first work stream, just going to move this. The first work stream, recycle, is really addressing legacy blades. What's the supply chain for recycling blades and what are the materials that need to be recycled? The second work stream, sustain, is around driving the use of more sustainable materials and processes. And the third work stream, design, is around sort of applying circular design principles and trying to be innovative in blade design, really to reduce waste and material usage, etc. So I'll just go into a little bit more detail on each of those work streams. I'm having to move my face around. So that first work stream, recycle work stream, as I said, is to drive and support the creation of a viable cross-sector supply chain for recycled composites from blades. And there's kind of 5 key work packages within this work stream, and highlighted in blue are those work packages that are live at the moment. So the first work package is really about mapping where the blades are in the UK, what generation are they, and therefore what materials are they made from, and when are they going to become decommissioned. And that's going to help us to understand what the sort of, I want to say raw material, not waste material, so what the raw material streams we have to work with when these blades come out of decommissioning. So that's what the first work package is around. The second work package is around recycling technology, what the landscape is like, what technologies are available, what's relevant and applicable, and what should we be doing in the short term and the long term. The third work package is around assessing the viability of that supply chain and understanding whether there is a supply chain for this recycled material, and if there isn't, whether recycled materials from blades can be used and be relevant to other sectors, and looking more broadly. And then the fourth live work package at the moment is around standards and design guidelines for recycler from wind blades, because actually there aren't really any. So we see that as a really important work package as well. The second work stream, which I'm involved in, is the sustain work stream. And it's really around facilitating the wider adoption of alternative lower impact materials and processes. So it could be fibres, resins, core materials, adhesives, for example. And there's 3 key work packages within the sustain work stream, 2 of which are live, and they very much go hand in hand with one another. I'm not going to go into loads of detail about that because that's where I'm going to delve into a little bit more later on. So I'll cover that one later on. And then the third work stream, design, as I said, is really about incorporating circular principles into the design of future blades. This is an earlier phase work stream, so it's literally just kicking off at the moment. And one of the live work packages at the moment is around understanding what circular design principles are out there and have been tried and tested. What strategies can we apply to novel blade design, essentially. So that's kind of a whistle-stop tour to SUSWind and the sort of research activity that's happening. But SUSWind is also about bringing together stakeholders from across the wind energy supply chain and sector, and also from across the composites industry, to make sure that we're bringing all of those different perspectives in to help us solve this challenge. So as we mentioned, SUSWind is not just the NCC, it's been delivered in partnership with the Offshore Renewable Energy Catapult. And we've also got a number of commercial partners on board that sit in different areas of the supply chain, which will be really valuable, from blade manufacturing to energy providers, for example. And we're also being supported by the Crown Estate, Renewable UK, BVG Associates and Net Zero Technology Centre. And before I move on to the next section, I just wanted to say, if anyone is interested in being involved and learning more, maybe you're developing materials or technologies that are exciting. They don't necessarily have to be relevant to wind. Or perhaps you work within the wind industry and maybe feel that your perspective hasn't been represented, then please do reach out to us. Our program lead, James, he'll be happy to hear from you. So yeah, please do get in touch with us. So I will move on to the sustain workstream that I was talking about. So the reason I'm going to talk about this today is because this is an area where I'm more heavily involved. And this work stream, as I said, has three strands, 2 of which are live. And the work package that I'm involved in is around assessing the impact of alternative materials. So when we talk about alternative materials, we mean any material that could be used in a blade which has the potential to lower its impact at any stage of the life cycle, across the blade's life cycle. And when we talk about assessment, we are referring predominantly to using comparative life cycle assessment to understand the environmental saving or burden that the adoption of that material will have on the blade impact. And in order to be able to run that comparative LCA, having a baseline LCA impact value for a reference blade. In our case, we're looking at a 15 megawatt, I can't remember the length, plus 100 meter offshore blade. So we're generating a baseline LCA for this reference blade, and we'll then be running comparative LCA of our materials, alternative materials, versus this baseline blade at the top level. Excuse me. So these two workshops work very much hand in hand with each other and rely on one another. I'm just going to have a drink. So I think it's always important to ask why are we doing this? Why is it important to assess the impact of alternative materials in the first place? So it's a really exciting time to be in materials development at the moment, particularly when you're looking at sustainability. There are loads of examples of really interesting sustainable materials being developed, not just within composites, but more widely across all different sectors. What we're seeing in composites is there's many materials being developed. Often they can adopt various different impact lowering strategies, as we're calling it. It could be that they lower impact at end of life, or it could be that they lower impact at material production phase, or it could be both. And also a lot of these materials tend to be at differing stages of development or certification. So the challenge that kind of brings about is that it's not always black and white to know, for a blade manufacturer, for example, to know which material they should invest in or develop or spend their time on. So the aim of this work package is very much about bringing clarity to that challenge, and we are tackling that in sort of a three-stage approach. So the first stage is about capturing what's available. So what's commercially available, what resins, what fibers, what core materials are available that have the potential to lower impact, and what are their performance properties as well. The second phase is around that comparison. So running the comparative LCA of each material against the baseline to see whether there's an environmental saving or burden. And then the final stage that we're hoping to achieve is to build a sort of tool set which compiles 4 different elements. So it compiles information around the technology readiness level of these alternative materials, what the environmental saving or burden is of adopting that alternative material, what the economic burden or saving may be, and also what the performance, maybe knockdown or improvements are. And the aim is that we hope that having that full picture and that transparency about alternative materials will help in decision making. So in terms of the top level sort of value that we hope we'll bring with this work is we hope to speed up the process of novel material adoption by the industry by bringing that transparency. And we're also not trying to maybe put one material on a pedestal over the other and say it's best. We hope that this work, that may be the case in some instances, but we hope that this work and the transparency will allow us to support perhaps material developers to improve and develop their material offerings, to boost their environmental ratings, or to help them understand where maybe the pinch points are in the supply chain to facilitate a quicker uptake of their material into industry. And the final hope and ambition we have is to just encourage a material supply chain where LCA and transparency does take priority. You know, it'd be great to see LCA impacts being readily available and as readily available as a material data sheet, for example. So that's the value we hope to bring. And I'm probably running out of time, so I'm going to be quite quick on this, but I want to just give a quick kind of summary of how we're getting on, because it is still early stage. So far we've collated our databases of alternative materials, and that's just a little nudge to myself. If you haven't heard from us or we haven't spoken to you and you're doing something really interesting, again, please do let me know. We'd love to include you. So we've collated these databases, and at the moment we're developing approach, and we're close to sort of finalizing our approach to how we do these comparative LCAs. So these last 2 slides are just around some of the considerations that have come up and that we're having to think about in terms of defining our LCA approach. So this first slide is really around scope. So when we first started databasing our materials, we very quickly realized that materials can lower impact at different stages of life, of the life cycle, as I've mentioned. So say a recyclable resin, for example, may lower impact to the greatest extent at this end of life disposal phase, whereas a bioresin, for example, may lower impact to the greater extent at this material production phase. So they're in different places, and it's really important to understand where our materials lower impact so that we make sure that the boundaries of our LCA, i.e. cradle to wherever you want to go, are incorporated so that we fairly represent our materials. So in terms of our approach, we really are prioritizing that we go from cradle to grave, if not cradle to cradle with our LCA approach. There are challenges around doing cradle to cradle. So at this stage, we're cradle to grave to make sure we represent all of the potential of the materials that we have in our database. What we're finding is actually a lot of the LCA information, impact information that's out there is not lacking, but it may focus on maybe cradle to gate or just at grave. So that's quite a challenge for us. I'm nearly done, I promise, Mark. So they're just 2 points. And then the last 3 considerations that we'll come up against is, again, quite a lot of LCA impact data might focus on CO2 equivalent or energy demand. And it may be that with some of these materials, there are impact categories that are much higher, for example, land use or fertilizer use, when you're looking at maybe bio-derived materials. For long-term assessment of future materials, end-of-life treatment we're seeing is quickly becoming quite specific to material chemistries, where you're getting platform chemistries. So it may be that for each of your materials, you'll have a specific material, but also a specific end-of-life treatment. You have to be able to compare them side by side. What we are concluding that landfill should not be used as a baseline for end-of-life assessment, because it will mean that all of your end-of-life treatment processes that you're comparing it against will come out higher. And finally, blade simulation is really important for understanding how the blade bill of materials and therefore its LCA impact may change when you adopt alternative materials. Yeah, thank you. I finished there, but I appreciate that's a whistle-stop tour. So if you have got any questions, just pop them in the Q&A and I'll do my best to answer them. Thank you very much.
Super. Thank you very much, Jenny. That was a great overview of what is a very far-sighted and all-encompassing approach to the whole sustainability and blades. And the way I think you presented such a complex area of the 3 work streams and how they all are very equally as important, and none of those work streams can be done in isolation. It all has to be considered in toto. Yeah, credit to you, Jenny, for going to in depth where you could, given the time constraints. Thank you very much.
Thank you.
Our next speaker is from the University of Cambridge, Dr. Darshil Shah. Dr. Darshil Shah is a lecturer and assistant professor in materials and a senior researcher in the Centre for Natural, at the Centre for Natural Material Innovation at the university there. He works with scientists across disciplines, developing biomaterials as lightweight, sustainable, and structural alternatives to conventional materials for various application sectors. And without further ado, Darshil, take it away.
Great, thank you, Mark. I hope you can see the slide okay.
Yep, all good.
Great, fantastic. So I'll be talking to you about designing biocomposite blades. This is primarily based on work that we've been doing on natural fiber composites for the past several years, and also some of the application-oriented work we have been doing on making small wind turbine blades. So these were for 10 kilowatt systems or so. So I'll be talking about some of the progress, challenges over the past year since, and yeah, what we look forward to do in the future as well. So as Mark mentioned, I'm at the Centre for Natural Material Innovation, which is led by Dr. Michael Ramage. I work with colleagues in the plant sciences and biochemistry at the very small scale, trying to understand how natural materials come together, both for bioinspiration, so that we can devise our own synthetic materials that are more environmentally friendly, but also so that we can possibly take natural materials apart and put them back together in a way, engineer them for applications we want them to be used for. Also working with chemists and biochemists to, at the tissue scale, for example, to improve the durability or the local performance, such as stiffness or strength of timber for certain applications, and then also working at the architectural engineering scale for the application of these materials. So we focus primarily on plant-based materials. Here you can see timber as the main focus, but we also work on bamboo and natural fibers and their composites, for example. Now I've put a picture of a building over here because that's a big part of the work we do, but also because we often in our discussions talk about buildings as carbon sinks if we can construct them from timber. Similarly, it would be fantastic if towers for wind turbines were carbon sinks, and this is being now looked into. This is particularly interesting because as some of our colleagues from industry mentioned, in the total life cycle of a wind turbine, the tower and foundations have a huge impact on the overall carbon footprint of a turbine, in excess of 50% in some cases. So here, data from Vestas suggests that the tower, primarily made from steel, and even though it's recycled, that's about 25% of emissions. The foundations, primarily concrete, are 13%. And if we can replace the steel with timber, which is going to be lighter and therefore also reduce the amount of concrete required, that's a big win in terms of the embodied carbon of the structure, as well as the fact that, as Steve Eichhorn mentioned earlier as well, plant-based materials sequester, they store carbon because they have been absorbing carbon dioxide or carbon during their growth. So for example, Modvian, who are now bought out by Vestas, they have produced a 30-meter tower, which is of the order of 180 to 300. Well, if it were to be 110 meters tall, it would be storing, overall the net footprint would be about minus 300 to minus 400 tons of carbon dioxide. And even not including sequestration, the timber tower has a 90% smaller footprint than a steel tower. The properties that are of particular interest of timber are, firstly, like steel, you could prefabricate it, construct it in a modular fashion, but also its specific strength and stiffness are really interesting. And if you engineer it in the form of a laminated veneer lumber, as they have done, you can produce really strong materials. And Steve also showed you some work that has been done around the world on densified wood, which you increase the performance even more. And as we mentioned earlier, natural materials, biogenic materials have been materials we've been producing towers with for a long time. This is a Wicken, this is at Wicken Fen, close by in Cambridge. It's a smoke mill, 19th century, which would produce primarily using timber. Some of the interesting design details you also notice are that in both cases, the old version and the modern version, the first few meters are not typically constructed from timber. So there are things you can learn from it, and we're not talking about completely removing steel or concrete from our materials mix, but mainly about having more plant-based materials. So the vision is, what if we can also make the blades from more plant-based materials? And this would start from the agriculture of growing specific varieties or species of plants, fiber crops such as hemp or flax, and then processing these using agromachinery techniques and techniques that we have developed over thousands of years in textiles for weaving, etc., to produce the fabrics or preformed reinforcements, which then we can impregnate with thermoplastic or thermoset resins to produce composites with properties that we desire. And so that's the vision, but there are some challenges along the way, which I will try and discuss and describe. There are lots of biocomposite precedents currently. So these are some of the one-off products in the market, from surfboards, a lot of leisure products, and in the mobility sector as well. As Steve Eichhorn mentioned earlier, apart from the lightweight, so plant fibers tend to be half the density of glass fiber and even lower density than that of carbon fiber, and their vibrational properties, their acoustic damping is really interesting. In fact, their damping factor can be 3 to 10 times better than that of carbon fiber and their composites as well. But the key, in terms of their precedence, you see some of these examples over here. However, the biggest sector that uses biocomposites today is the automotive sector. I think around 10 to 15% by volume of the automotive sector accounts for the total composite sector in the world. So it's a much bigger market than carbon fiber composites in terms of volume. And as we know from the building sector, volume and the supply chain is an important part of whether we will have enough materials to be able to produce wind turbines or other applications. Natural materials also tend to have multiple streams that they go into. So it's important to realize what stream may not exist if you were to divert the routes of the end streams. There are a few other biocomposite precedents. A lot of these are historic, and Henry Ford, which we now know was actually developed by Washington Carver from Steve. Thank you, Steve. Produced these soy-based hemp phenolic soy resin hemp composites for their Model T car, and Spitfire fuselages from Gordon Airlight, which is a flat phenolic composite, noting the bauxite ore shortages or potential shortages in case France was invaded at that time. And I think in both cases, a few prototypes were developed as well. And more recently, we've also heard that a natural fiber nacelle case, 7 meters in length, is going to be produced for offshore wind turbines in a partnership with Cyclemin, who produce their green epoxy resin, and BCOM. So slowly but surely, natural fibers and bio-based materials are penetrating the wind energy market, which is good to hear. And we've been working with flax and other fiber-based materials for several thousands of years. In fact, the first bio-based composites were materials like these cartonages, which used linen, flax with plaster, even for wrapping mummies, for example. And there are lots of beautiful paintings that you can see how historically these materials used to be produced, processed. The important thing to realize is that even though natural fibers are of interest and are almost exclusively used for the automotive sector for interior panel components, only about 3% or so of the flax fibers that are produced in Europe, for example, actually go into composites applications. The wide majority of them go into things like fashion, for making clothes, but also for making paper, for animal bedding and things of those sorts. So a diversion in these end products is necessary. And nevertheless, natural fibers are technical fibers, and apart from their low density, impressive vibrational properties, you can get quite impressive tensile behavior. So in terms of their stiffness, you can achieve up to 80 gigapascals, and even strengths, you can get 800 to 900 megapascals, about half that of glass fiber, relatively easily. Silk is another fiber we are interested in, which is important or useful for more toughness critical applications. So for a structural wind turbine blade, the key parameters that are necessary to design for are their life of 20 to 30 years, fatigue loads. We looked at small wind turbine blades, which actually rotate at 200 RPM rather than 20 to 25 RPM for the larger wind turbine blades. So the fatigue loads can be quite phenomenal, but also static loads in terms of extreme wind conditions and the fact that these materials need to be tested at the full scale for applications. And we have some data on this in a paper if you want to look at that later on. But we tried to design and construct an 11 kilowatt turbine blade, 3.5 meter long, with a traditional construction architecture with a composite shell, so a foam core for buckling, and blister caps with axial, with a unidirectional and triaxial fabrics. So for optimizing the properties of this biocomposite, some of the things we could change were either the fiber, the matrix, the orientation, the volume fraction, the mix of the fibers, as well as, yeah, I mentioned the orientation. There are a wide variety of plant fibers available to us. We primarily looked at bast fibers because in nature, the function that they have is actually to support the structure of the stem. And within this, if you look at this Ashby diagram, you quite clearly see that bast fibers such as flax, hemp, and jute have stiffness and strength that is higher than most other fibers. I think Coara fibers or pineapple leaf fibers are the other interesting ones, as well as banana leaf fibers, which are extremely long. But some of the key properties at the microstructure level that give them these high tensile properties are their cellulose content, crystallinity, the low microfibril angle. Natural fibers can be porous, so you want less porosity, a luminal porosity that is non-existent almost, and high aspect ratios. So we eventually went with flax fibers because it is also one of the industries that is most developed in terms of the textile materials that are available or can be produced from them. There have been lots of advances over the past centuries, particularly in agrobreeding. So this is a hemp stock, and you can quite clearly see that since the 1960s, we have worked quite a lot to increase the yield of plant fibers, but also changes in approaches to, for example, for retting, rather than pond retting, we now use dew retting or field retting because it's more environmentally friendly rather than polluting our waterbeds. There have also been advances in preform processing. Several years ago, you wouldn't be able to find weaves and unidirectional prepregs specifically for composites applications, but now that is possible, although there are still only limited types of preforms available. But even so, you can reach strengths of up to 400 megapascals in terms of composites and tensile modulus of 40 gigapascals. One of the other limiting factors about natural fiber composites is you have a critical and maximum fiber volume fraction, which is a narrow window within which you can process. And it's quite hard to produce plant fiber composites in excess of 50% fiber volume fraction, which presents some challenges for the wind turbine application sector, as well as because plant fibers have a nonlinear stress strain response, you see that there is a stiffness drop in the first few percent strain that is applied, and that needs to be considered during the design of a wind turbine blade. I'll quickly rush through some of the testing that we did. So we made a full-scale blade, which was about 10% lighter. We couldn't get higher, more fiber in it because it was lofty. And I mentioned about getting fiber, lots of fiber in there being a challenge. The other aspect was during the testing, we quite clearly realized that although the flax blade could surpass the necessary worst case and normal survival loads based on the IEC 61400 standard, we noticed quite clearly a nonlinear stress strain tip displacement behavior. And this would in theory be a failure because of a stiffness drop, or actually it would hit the tower because of the tip displacement. So those are things that we still need to design and develop further. There's a lot more in a recent review that we have done as well, and also some work we have done recently on looking at smart silk composites, for example, by functionalizing the fibers so that the fibers can act as sensors as well. So how we can use natural materials to both reinforce, but also for structural health monitoring. I think I'll stop over there. That's okay.
Thank you, Darshil. I appreciate there was a lot of content there. I'm itching to ask some questions, but I'll invite everyone on the call to please put some questions in the Q&A. I'm sure the audience has a number of questions, and we'll endeavour to answer them if it's directed to Darshil or anyone else, because we have limited time for the Q&A at the end. So moving to our next speaker. Is Professor Ian Hamerton from Bristol University. He's Professor of Polymers Composites within the Department of Aerospace Engineering at the university. He holds the chair in Polymers and Composite Materials at the university. He is a chemist by training with a PhD in high performance polymers and some 30 years experience in the design and characterization of advanced polymers. Since joining the University of Bristol in 2015, he's expanded the scope of his research to encompass materials for wind turbine blades and co-supervises a couple of PhD students in the area within the Wind Blade Research Hub. And yes, Ian, I'll invite you to start your talk.
Super. Thank you very much, Mark. It's a pleasure to talk to you this afternoon. This is a fascinating topic, and there's been already some excellent presentations. It's a real delight to be part of it. What I'm going to be talking to you today is about looking towards how we try to get an idea of how long the blades may last. So not a direct aspect of material development, but this will involve looking at the next generation of materials. I'm going to look at this very, very briefly because coming late in the day to the presentations, the context has been very, very well set. So I'm going to take it as read that there are challenging targets, but one of the principal drivers behind this work is to develop cleaner energy globally. And as you can see, the targets that have been set are very challenging, but also the way in which we're meeting that, there is some variability in the way in which nation states are managing to tackle this challenge. The other aspect is not only reliance on greater reliance on wind energy, but also increasing wind energy production, coupled with this growth in turbine blade size. And I just want to highlight this image here, where you can see that both in terms of power output and also in terms of blade length, from a 15-meter blade in 1980, you can see we're around in the 2020s, where we're talking about at least 200 plus meter, potentially 200 meter plus blades, and the Siemens Gamesa SG 8 megawatt turbine blade has already been described, which has a rotor diameter of some 167 meters. To put that into context, this image you see on the right-hand side here is of a 70-meter diameter turbine blade superimposed with the Boeing 747 jumbo jet. So you'll see the comparable with the span, the wingspan, and nose to tail length of a jumbo jet. So these are big structures we're talking about now. But what I'm going to focus on is looking at increasing blade longevity and understanding more about leading edge erosion, which, as you can see from this image, is potentially a big problem. Not only a financial problem, it costs the European offshore wind industry, as you see, somewhere between 50 and 70 million euros annually. So it's a big potential soak for cash, but also the need to effect emergency repair means that unplanned downtime for wind farms can be a real problem. So what causes this? Well, this is impact with rain droplets. Now, given the velocity of the tip speeds in wind turbine blades, rain impact velocities are at least 100 meters per second. So repeated impacts, particularly in heavy rainfall, means that you get a lot of force essentially on the blade. The impact of this, literal impact and long-term impact, is to reduce the blade lifetime, reduce the dynamic performance. And as a consequence, there is not only a limitation on the speed of the turbine, and as a consequence, a reduction in the power output, but also the costs of programming inspection repair programs are also significant. As you can see, over the lifetime of a turbine, these can really add up. It sounds a small thing, but rain droplet erosion is potentially a big problem because of the repeated high-speed impacts. And you can see in the schematic on the left-hand side here, the impact on a surface of the blade essentially evokes several wave responses. Initially, a longitudinal compressional stress wave, preceding transverse shear wave, and then a Rayleigh wave at the surface, a surface acoustic wave from the force rebounding back from the coating. So the combination of these waves causes a lot of stresses, compressional and shear stresses within the materials. And so consequently, these lead to the characteristic delamination, debonding that I showed you. And this can be a real issue, particularly when you're looking at modern current protection systems. Here's a schematic showing a section through the turbine blade. So we have the structural fiber reinforced polymer composite at the base, which will be glass fiber reinforced polymer in the context of smaller turbine blades, and increasingly for the longer structures, carbon fiber reinforced materials, covered with a filler and then a top coat, and then the leading edge protection. So it's a multi-layer structure. Each of those materials are really quite dissimilar. They have very different mechanical, elastic properties. They have quite different acoustic properties. Transmission properties differ greatly. So we're designing this structure to last some 25 years, and the materials that we're putting onto those structures don't have that sort of lifetime in pristine form. So regular repair, replacement is inevitable, and so consequently what we're trying to do here is to understand, have a greater understanding of the materials that we're using, and as a consequence improving the modeling methods to understand the lifetimes of those materials, and to try and understand more about when those materials might usefully be repaired or usefully reduced or removed from service to enable replacement to take place. And so this is about understanding the material properties, improving the test facility, because the move generally has been away from metallics through harder polymers and increasingly softer, more elastomeric materials. So these are structures which will be a little bit more rubbery in their appearance. So you might see typically polyurethane, cross-linked polyurethanes at the surface. This example here shows you a typical rain erosion demonstrator mimicking the leading edge of a blade. But in moving towards these newer materials, the problem is much of the understanding of test facilities and also modeling methods is rooted in a much older technology. And so consequently, part of what this is about is to understand improving the test methods, and also not just improving the test method, but in developing more informative prediction methods. So less simplistic, more dependent on the material properties. So for those who have not come across the concept of a viscoelastic material, if you've bought a bed or a mattress in the recent history, you probably will have come across the concept of a viscoelastic shape memory foam, and you see that sort of illustrated here in this image. The issue here is that viscoelastic materials, as the name suggests, have both viscous and elastic behavior. And very simply, if you apply a constant stress to such a material, then over time it gradually deforms. The strain increases with time, the material undergoes what we call creep. Whereas if you hold the material on a constant strain, then over time the stress decreases and the material relaxes. So these materials are quite dynamic, and that in itself presents quite a different idea in terms of how we test and evaluate them. So this strain rate dependence is key, as is the temperature dependence. So not only is strain rate key, but temperature of analysis is also important. And you can see that in these classic analysis, classic schematics showing how those properties change. So on the left-hand side here, you'll see this is looking at essentially elastic properties modulus against temperature for a typical viscoelastic polymer. What you'll see is, whilst we're conditioned to think in terms of what we call the glass transition temperature, you change from a glassy to a rubbery material, there are also a series of different changes where you get molecular motions, be they small, short scale, slightly larger, longer scale changes, and effectively slippage in polymer chains over one another. So each of those has quite a profound effect on the mechanical properties, such that material can be quite stiff at certain low temperatures, and become quite soft and compliant as the temperature increases. So the key point here is that turbine location will change the properties of the coating in the matrix. So we have to be very, very aware that a test performed needs to be performed at an appropriate temperature that reflects the use temperature. Similarly, if we look at the impact, the frequency of impact, then as we apply a load, again, the modulus changes such that the material may have more solid-like features at low frequencies, represented here by a dash pot, whereas the material may perform more like a solid, less like a Newtonian fluid, as the frequency of impacts increase. So again, the impact frequency is going to change the properties that we observe. So we have to take those into account. And we're working still with relatively old traditional models. So the Springer erosion damage model, which was conceived in the mid-1970s, is still most commonly used prediction model to determine brain damage and consequently lifetime. It's largely based on changes in material acoustic impedance, because we're talking about the propagation of a wave, which will be transmitted through one material through an interface, a boundary, into a second material. And so the acoustic transmission and reflection behavior will determine how well the energy of impact is dispersed and propagated through the material. And you can see here this is how the speed of sound is calculated. You'll see that the elastic constant is quite key here. So elasticity of the material is going to be important. And also, when you look at the acoustic impedance, the importance of the speed of sound is also key here. So we need to understand these properties really well for the materials that we are designing. How's this done traditionally? Well, currently it's very much a pulse echo technique. So a probe is applied to the surface and a pulse is transmitted through the sample. It hits the back wall, it comes back as an echo, and you can see that as a quite sort of simple sort of test here, carried out at one frequency, typically 5 or 10 megahertz. And that distance enables us to calculate the speed of sound as simply the distance traveled over the time of flight. Now, this is nice and straightforward if you're talking about metallics. You can see a nice clean spectrum where the distance between pulses is nice and clear. As we start to move into viscoelastic materials, on the other hand, these become far more complicated. And if we look at the three areas here, this very complex structure at the center, on the extreme left, is crosstalk. So this is quite essentially a complication of the signal through the molecular structure. As we increase the thickness of the film, of the protection, then the signal becomes more attenuated, and we start to find it difficult to determine signal shape and position. On the other hand, as we start to go to thinner and thinner structures, then the interference becomes more problematic. So this raises the question, really, are we doing this in the right way? Can we really quantify the speed of sound at a single frequency, single temperature? Is that enough to capture response to enable us to understand how well these materials are behaving? And can we say anything about their longer lifetime? So the move with viscoelastic materials has been to shift towards the use of dynamic mechanical analysis. And this is a simple sort of structure here where a beam of the material, be it composite or coating material, the polymer, is held in secure clamps and then is vibrated using a sinusoidal force from this movable clamp in the center. That produces essentially a plot of either the force or the displacement. In the case of a purely elastic solid, this is in phase. We get a nice tie between the applied force and the displacement. With a purely viscous liquid, we get an out of phase, a 90-degree out of phase response. Because we're talking about a viscoelastic material, it sits somewhere between the two. So we get something where we can measure the damping, this delay that is introduced. So over time, of course, the DMA is relatively limited in what we can do to test this. So we actually carry out a series of analyses at different temperatures. These give rise to different behavior to monitor how the modulus changes. And then we can simply construct a master curve from all of these data sets. That in time gives us a master curve, and you can see that carried out for 20-degree analysis here for different moduli, the storage modulus, the loss modulus, and the tan delta. And this tells us about how well the material stores energy, how well it dissipates energy, and what its damping characteristics are like. So if we can understand more about its damping characteristics, we can determine whether it's going to be more efficient as a coating for us under these conditions. So this gives us our master curve, and as you can appreciate, if we do a single test using the single probe, we actually find we can measure the speed of sound, but this is, in this case, at 5 megahertz. It bears little relation to what we see across the whole range of the properties of the material. So what this means for us is if these values here in red are the single measurement for the NDT data, they bear little relationship to how those data, be it the material strength or the impact pressures, change as you begin to shift the speed of sound. You can see the same for the comparison of the number of impacts. We've got a single value down here, but the DMTA value was allow us to extend that over a wider range. So what does that mean for us? Well, it means that if we are able to move beyond this single plot, it indicates that the minimum impacts of on a coating before failure could be seriously underestimated. We could be talking about a value that's 5% lower than the NDT method. Conversely, the number of impacts that it could withstand could be significantly higher. So being able to sharpen this model to reflect this gives us a better range of understanding. So I'd like to thank Imad Ushan, who's the PhD student whose work this is based. He's supported by the EPSRC CeTeC within the Bristol Composites Institute, also some work from the Future Composites Manufacturing Hub and the BLEAR project, which is a joint industry project led by the ORE Catapult. Thank you very much for your listening, and I'll be more than happy to answer questions in the chat later. Thank you, Mark.
Thanks, Ian. I appreciate there was a lot of work to get down to, but just to highlight very, very quickly for the audience for some context how important is in the whole sustainability realm, clearly that we develop materials that last longer, because clearly if we can get more lifetime out of the assets, that's the best result overall for sustainability before we took the long-term view of materials and the energy inputs into the production of those materials. Thank you very much, Ian.
Very welcome. Thank you.
Our final speaker today is Tomas Flanagan. He is the CEO of ORE Composites in Galway, Ireland. He joined as a Marie Curie Research Fellow in 2014 and was a principal investigator on several Horizon 2020 and ESA projects. He has a PhD in engineering management from the University of Cambridge, has previously worked for BP and Boeing, and I believe he'll speak today on the manufacture and testing of large composite structures. Thanks, Thomas.
Hi everyone, can you see my slides?
Can indeed, sir.
Very good. So just to give an overview, I'm going to talk very briefly about the company, just then talk about the wind blades that we manufacture here, going to talk about powder epoxy technology, and then a couple of the research projects that we've been involved in. So ORE Composites is a design, manufacturing, and testing company that works in aviation, space, and renewable energy. We've got approvals for aerospace manufacturing, and we've done a lot of work on Horizon 2020 projects and FP7 predecessors. We manufacture blades up to 14 meters in length, which is pretty small by the modern standards, but it's big for, say, a research lab. And we make some smaller blades as well from glass fiber polypropylene, which is thermoplastic material, which is recyclable. And then we manufacture tidal blades, aviation structures, and components for satellites. Recently we were awarded a contract for the stray light baffles on the LTS satellite, which we think is pretty cool. So that's just a slide of some of the research partners on different projects that we've been involved in. The production blades these are the small black blades you see on the right. And the picture is actually in Antarctica. So these are made using heated metal molds and processed around 200 degrees. And the Twintex material, the polypropylene, it's good for this kind of smaller blades, but it doesn't really work for the higher loads on the bigger blades. So the 13 and 14 meter blades were made with glass fiber and powder epoxy resin. And I'll talk a bit more about the powder epoxy technology in the next slides. So most blades are made from liquid epoxies or polyesters, but we've done a good bit of work on powder epoxies, which is obviously solid state. And we use that to make wind blades and also parts of boats and some other structures. And we've used this to make production blades up to 14 meters. And we developed a line for taking the dry fibers and adding on the powder epoxy for different fabrics. And we achieved fiber volume fractions of about 55%. Some of the advantages, you get really good wet out, especially for thick sections. You have reduction in post-processing requirements, reduction in material wastage. The material can be processed a lot like a pre-preg material, but it's more suitable for transport and storage. It doesn't need to be stored in a refrigerator. And it's potentially a good matrix for use with carbon fiber, which is difficult to infuse because the fibers are smaller than glass. So then the powder blade project was a Horizon 2020 project which was led by ORE Composites, but also included Westbic, which was a local business enterprise company, Suzlon, which are large wind energy company based mainly in India, but with a lot of research in Europe. The University of Edinburgh were also part and did a lot of the testing work, and we'll have some slides on that later on. And the idea was to look at the spar caps within the blades and also the blade roots. The first thing was to design and manufacture carbon fiber spar caps and blade root section, to develop a computational model for the cure cycle, design and test torsion box to reduce cycle time for blade production, and commercialize the powder epoxy technology. So a lot of the work on the computation modeling was done by the University of Edinburgh in Professor O'Grady group. And they used Abacus to make models of very thick laminate sections, so 96 plies and about 15 centimeters thick, and then looked at just how the material heats up. So we will be using heated molds or ovens for this, and I guess usually you get the reaction within the composite, so that it heats from the inside out due to chemical reaction. We're heating from the outside in, which is a bit different and has some implications for just the thermal stability of the products at the end. So we made a glass fiber root section that was for a full-scale 54-meter blade. It was 96 plies thick, and we didn't have any problems with dry spots. We also used temperature probes within some of the smaller test panels in order to validate the computation model, and we got good correlation. Also, we made some carbon fiber spars, so we made these up to 13 meters long, and they're about 10 millimeters thick. And the first efforts, we had issues with the alignment on the fibers, but we actually resolved that subsequently and got pretty good fiber alignment. So I guess technically we know that the solution is pretty good, and it's about building the business case around it. So then we built a torsion box, which was it was a scaled down version of a 60-meter blade, which was designed by Suzlon. So it had a glass fiber root and a carbon fiber spar, and transition from glass to carbon. And that was tested at the University of Edinburgh, and we got pretty good correlation with the analysis that we've done. And like it was pretty detailed test. A lot of data was captured, and the behaviors just between the glass carbon interface, it's something that doesn't get an awful lot of discussion in the literature, but that is a pretty big problem for industry, where they're trying to make blades that you've got carbon for the load-bearing elements, but glass for the on the root section where it's thicker by definition. Also, the stiffness is another advantage of the carbon, because it reduces the pre-bends that you need for the really big blades, going sort of 60 meters plus. So that was a quick tour of the powder blade project and the powder epoxy project. And the next one is much more closely related to some of what Ian was talking about, Professor Hamerton, on leading edge erosion. So we found some papers that said that erosion causes losses of between 4 and 20% of AEP. I think 20% is probably a bit high, but in environments where it's hard to service the blades, particularly offshore, it's a problem. Also, again, offshore blade repairs become dangerous and expensive, and you've got issues with weather windows. And as the blades get even bigger, it become even harder to service. But also, the larger blades tend to have higher tip speeds, and this is a problem facing the industry, that you can make the blades bigger, but you may be limited by your tip speed in terms of erosion, and trying to avoid damage to blades. So we're looking at, again, Professor Harrington touched on it. There's some advocates of kind of metal coatings, like helicopter blades, and then there are other people looking at sort of softer solutions like thermoplastics. So we were looking at thermoplastic coatings to try and reduce erosion as part of the Leap Wind project. So the solution then was to come up with something that was recyclable, UV resistant, good energy absorption, and was thermoformable to the geometry of the blade. The last one was actually one of the more challenging parts of the project. And again, this was touched on the previous presentation, but finding representative tests is difficult. So we did testing at a lab scale, and on coupons about the size of a £2 coin, say. And some of those results it's difficult to tell how well they correlate with the real world scenario. The adhesion between the protective coating and the substrate is a challenge. And so there are some protective materials that are good in terms of stopping erosion, but you need to be able to get them to stick onto the blade. And the shock waves from the impacts from raindrops are passing through and to the substrate. And if you have different materials, you're likely over time to get deterioration on that interface. So we were looking at those kind of things and looking at existing solutions that are used commercially and trying to figure out whether there are opportunities to improve. So we did some trials in the lab. We also did, we made some blades and put them on a small wind turbine in Shetland. We tested a blade with the market leader, which is 3M, leading edge protection. We did an uncoated blade, and we did thermoplastic polyurethane, which was the solution we were looking at the most. And like the trials showed that there was some damage on the unprotected blade, but it was pretty early on in the trials. So really you'd expect to see damage probably after a year or after a couple of years. And so the trial is still ongoing. It didn't flag up any problems, but also didn't demonstrate conclusively that the leading edge protection solution that we delivered was fit for purpose in industry. So we're continuing with the trials. I do think, though, that it's an area that warrants further research, and that there will be opportunities in the future. So then, I suppose there's a massive growing market for leading edge protection. Leap Wind developed a solution to look at this. It was tested in the laboratory, and field trials are also done. And it's a technology that is disruptive. A good solution would be useful for Europe and for sustainability. And there's been some talk about recyclability of blades, but one of the best ways is if you can extend the blade life and extend the turbine life, because you're creating green electricity, but without any of the costs associated with decommissioning or even installing a new turbine. So then just going to very briefly mention a few other projects, and I think I'll probably finish slightly early. This is a project, it's the Crimson project on tidal energy. And the picture in the background, what you've got is a tidal turbine, which has helical blades, which were manufactured at ORE Composites. So the green parts, the struts were made with glass fiber and powder epoxy, and the black parts are carbon fiber powder epoxy. So they're helical blades, and the whole device is about 10 meters long, so it's 2 by 5 meter sections. And that's an existing device that's been installed in Alaska and operated successfully for 2 years. We're now building the successor device, part of the Crimson project. So we want to further de-risk the technology and design and manufacture a newer version of the device, prove the structural integrity, and perform operation trials at full scale on the device. It's a really interesting technology. There's a step to go from even this scale, which I think was 30 kilowatts, up to sort of megawatt scale. But if we can prove that it works with the partners ORPC and Galway and Mitsubishi Chemicals are providing recycled carbon fiber for that turbine, then we think there's a really big opportunity. Then another project was FlowTech, which is, I think, literally ended last month. It's a 9.8 million euro project led by Orbital Marine Power. So we did work to develop an 8-meter blade for the turbine using powder epoxy again, and that was tested at INUI Galway. So full-scale test. So it was the largest blade to be tested in both static and fatigue. And again, we got good results between the good correlation between the computational models and the test data. And we're involved in a new project which is Merwind. It's led by Luridera in Spain, and it's looking at novel materials to reduce costs and extend the life of offshore wind. It's looking a lot at floating wind as well, which we think is probably not the immediate future, but it's the next big frontier for wind energy. And it will build on having better work for leading edge erosion protection and better materials such as the powder epoxy and better manufacturing processes for scalability. So I think that's everything I wanted to talk about. Thanks to everybody for listening, and if you have any questions, please go ahead.
Thank you, Thomas. I just had a question, actually. I was wondering, in supporting the powder-based production process you're using, do you feel that there's adequate marketplace choice in regards to bio-based epoxies, or you were looking at different systems apart from epoxies?
No, like there isn't really. Like there is, I think it's coming, and I think the European Commission are trying to encourage increased use of bio-based materials, but really a lot of it is still, it's very early stages. And I think one of the things that's a little bit difficult to grasp is the size. Like wind turbine blades are big, and you don't get to do it by halves. You can't, you're looking at tons or tens of tons of material in a blade. So you don't want to try bio-based material unless you're really, really sure that it works. And I don't think that that exists yet. I don't think people have the confidence in the bio-based materials. And I think it's similar for the thermoplastic blades. I think there's been a lot of really good work done by Arkema on helium, and they've got they published work about 13-meter V27 blades, and I think they've also done now a 25-meter blade that has carbon fiber spar, but the carbon fiber was with epoxy rather than helium, I'm nearly sure. And I think it's coming, but it's still a bit away. That'd be my view. But I really think it's needed. There's a big drive from the Green Deal, from a lot of the European governments and other governments to have sustainable sources of materials. And once they're proven to work properly, I think companies will demand them.
Super. Thank you very much. I'll just look at some questions in the chat here. We have a question from Alexander. How does the strength and toughness of your powdered epoxy in the bulk and in situ FRPs compare to current ones used in infusion of wind turbine blades?
Like we have some data on it, and some of it's been published in papers, but I guess the properties are pretty the same. Like it's fundamentally it's an epoxy resin, so you end up with similar properties to if you're using a liquid infusion resin. I think we're hopeful that for carbon fiber, because the big advantage is you're not trying to infuse through the thickness of the part. So for thick parts, you avoid issues like dry spots, but you should be getting the same properties as you would get with an infusion where you don't get any dry spots. And that's what the data shows in the testing we've done.
Yeah. We have another question from Maria. Hi, Thomas. Thank you very much for your presentation. Would the powder resin be applied in a pre-preg style or be applied during manufacturing?
It's a really good question. So what we've been doing is a pre-preg style. So we take the powder, we add on, we take dry fibers or fabric and add on powder to make something that essentially is a kind of a pre-preg or a semi-preg. Then we cut that into shapes and lay it up on a mold. So it's quite like using a pre-preg. And there's also a stage in the process where we call it like B staging. So you can heat the material so that it melts, but it doesn't cross-polymerize. So it takes up the shape of the mold and it becomes a solid prefabricated part that you can move or lift out of the mold or turn upside down. But it hasn't yet been cured. So you can co-cure the different sub-elements of the blade. So the top and bottom skins, the root, the spar caps together. Yeah, kind of like, and sorry, there is a second part of that is we are kind of interested in using it as a tape. So again, University of Edinburgh has done some work on this, manufacturing tapes with powder epoxy and heating them so that the powder melts as you process it, and that would allow a higher degree of automation. But that's very early stage stuff, I'd say TRL 3 or 4.
Indeed. Right, thank you for getting us back on track too, Thomas. I think you deserve, as well as the other presenters, a good, 9-minute break now. So we've got a break, and if we could reconvene everyone at 4 o'clock, 1600, for an industry panel discussion, yeah, that'll be great. Thank you, one and all.
I think it's 4 o'clock now, so I wonder whether we could get the industry perspective started. So, and the discussion. So my name is Steve Eichhorn. I'm Professor of Material Science and Engineering at University of Bristol. Those of you who were around earlier will have heard me talk. And it's my great pleasure to be able to chair this panel. You'll see that we have 3 other panelists. We have Lorna Bennett, who's a project engineer at ORE Catapult, Dr. Pierre Stefan, who's a research engineer at EDF, and Dr. Mie Elholm Birkbak, and she's a specialist in innovation and concepts at Vestas Wind Systems. So the floor is open really to ask questions of our experts, and I mean, in view of just sort of getting the discussion going, I thought I'd start by asking Mie, what new technologies being incorporated into the future designs processes are you most excited about?
Well, in general, I think it's hard to put sort of a a single technology in the spotlight. In many sense, I think all of this sustainability challenge is like all hands on deck. And I think we need to look into multiple different perspectives. For example, I see a lot of the potential for recyclability marrying the biomaterials coming up. I think we can develop those two tracks individually and then potentially, hopefully, sometime merge them. And in all of this, I think there's room for all the technologies. In general, I'm very big fan of the one addressing sort of this change from viewing these materials as a waste to a source of raw materials or something that can live on for longer times. And these technologies, I think they are very much needed and very soon. So this is something that excites me, that I see these popping up all around. But in general, I really think that this is a multiplayer game and that we need all the technologies that we have seen today.
Yeah, I've just been reminded, I've missed a step in this. I was going to give you the panelists a couple of minutes to introduce themselves. Okay.
Oh, yeah.
so perhaps you could just say a few words about yourself since you've got your microphone open. And
yeah, absolutely. So yeah, my name is Mie Birkbak. I am part of Vestas, and in this department of ours called Innovation and Concepts, basically where we have our eyes at all new technologies that are coming into the wind industry in the little longer time horizons, like 5 years or maybe even 10 years. And I have a background in biomaterials research. I did a lot of bones and shells and like hard inorganic material, biological materials, and have been working in the X-ray industries also for some years before joining Vestas not so long ago. Yeah.
Okay, thank you very much. Lorna, do you want to say a few words about yourself?
Yeah, thanks, Steve. As you mentioned at the start there, I'm a project engineer at the Offshore Renewable Energy Catapult. I have a background in mechanical design engineering, and for just over the last year, my main focus has been on the technical delivery of our projects, looking at decarbonisation, circular economy, net zero energy transition. So everything that kind of falls out of all of our mainstream projects. I think there's a few of the programs I'm working on that may have been mentioned already. So we've got our circular economy for the wind sector, which is looking at all the questions around life extension, sustainable decommissioning, recycling, end of life management, and our Energy Transition Alliance program in partnership with the Net Zero Technology Centre as well. So yeah, a little bit of everything.
Okay, thank you. And Pierre, just say a little bit about yourself.
Yeah, hello everybody. I'm Pierre Stéphan. I'm working at EDF R&D in France, and my background is mechanical engineering and materials, and I'm working at EDF for more than 10 years now on topics that are relative to monitoring of structure, but now also on all about blades topics, and that includes, of course, recycling. And before that, I have also worked on all about wear of materials and also erosion.
Okay, thank you. I'm just looking to see if we've got any chat questions. So please do add any discussion topics or questions in the Q&A as being requested. But perhaps I could start asking Pierre a couple of questions. So, what are your expectations about blades that are going to be recycled soon? And, what are the limitations today in the choice of a recycling process from a utility point of view?
Yeah, it has been already said in the introduction of this conference. Today, we are confronted to a lack of recycling processes for blade composites, and for an operator like EDF, there are only two solutions: storage and mechanical grinding. So this leads to limited reuse possibilities of the recycled materials, and so to the value of the blade almost zero, but not. So it is obvious that for EDF, the main challenges are not to get more possibilities to recycle the blades, and so to recycling processes that leads to better recycled materials in terms of mechanical characteristics, and so that could offer us a more diversified offer for components manufactured by recycled materials. And so the aim at final is to have blades that have a value as waste. That's it.
Okay, thank you. Yeah, we've got our first question in, and perhaps I'll put this to Lorna. You could start by answering this one. You know, what role can or should policy play in promoting more sustainable blades, do you think? That's a question from James Gilbert, by the way.
James, difficult question to start with. Yeah, it's been a hot topic of discussion and with various groups in terms of how much policy and regulation needs to lead the way to encourage the production of both more sustainable materials going forward, but also in how we deal with the, as here we're saying, the waste that's coming up. There's a lot of countries in Europe, particularly Germany, gets talked about a lot, where they've already introduced landfill bans. So blade waste cannot go to landfill, and the companies are being forced to find alternatives. The alternative that seems to be taking off there is the cement kiln co-processing, because it's seen as a way of helping decarbonize the cement, concrete sectors. But again, that brings the question of, is there something of higher value that we can get from the end materials that could be reused for something more than heat recovery and clinker? And there's a lot of discussions going on at the moment about how we might be able to reevaluate that lifetime cost and environmental assessments in terms of the processes that are currently being studied to develop these recycling techniques, but if they require a huge amount of energy and heat or other environmental impacts, is that worth it for the materials that we get out at the end? So there's a lot of discussion going on about, and particularly in academic circles and ongoing research, and in a certain extent, policy is often a kind of leading the way to encourage industry to take that step a bit faster. But it's obviously the wind industry are already thinking about their waste problem coming up, but they need other industries, cross-sectoral companies, to help them come up with the solutions to deal with the waste. And that's where we're having, we need something to pull the industries together to start these discussions, and events like this are a good way to start that.
Yeah, thank you, Lorna. Do Mie or Pierre have anything to add to that at all? Anything?
Yeah, I'll definitely back Lorna in these views. I think it would be key to gather more industries to sort of have the volume necessary to make a business case also out of this. Because if it's, I mean, in the wind industry, it can be pioneers and we can sort of show the way. But I think to drive the big wheels, we need to be a lot of people. And even though we use a lot of composites materials in the wind industry, it's only a fraction of the full amount of composite materials that go into the world today. And in that respect, I think policymakers can make a big difference of not making this only something for the few, but for the many. And I think that will help everyone dealing with composites to have that volume, also to make just a business case that makes sense.
Okay, Pierre, anything to add?
Yeah. I agree with his point of view. We need to be many of us to work on that topic, and but also to make different and many different recycling ways to arrive to an industrial point. Because today one issue is, okay, we have many different ways to potential different ways to recycle composites, but which one is or which ones are the most appropriate? Which one will be available in the different countries? There's many questions like that to answer also, and
yeah, okay, great. The next question, and I think it's what they're asking is they couldn't see any research on connection and joints, which are the most critical structural members in the blades. I think they mean couldn't see any research. So did perhaps somebody want to take that and address that, maybe talk about some of the research that is ongoing about joints and connections, or does anybody want to take that? I mean, we didn't really cover that area, which is true. We haven't really sort of talked about that. There's maybe something to pick up in a future program.
Yeah, I can just say very briefly that something that is important and that also relates to this is the weight of the structures that we put up are extremely important, because blades are, I mean, we spin them around with 100 meters per second, right? And introducing additional weights there, it will just have massive influence on both the tower, the foundation, and all of this. So I think I'm not sure I can answer this specific question, but at least I think it's important to include this research, because joints are, I mean, they can potentially be very difficult to keep on a low weight, for example.
Yeah, well, we know joints are particularly difficult when you combine composites with other materials as well.
Exactly.
And I think there's some things to be.
And the solution is not just to make it bigger.
No.
Yeah.
Next question is from Chris Harrison. Are European wind turbine operators prepared to pay a premium for recyclable blades? Good question, Chris. Anybody want to take that one on? Pierre, do you want to take that one on?
Can you just repeat the question, please?
So the question was, are European wind turbine operators prepared to pay a premium for recyclable blades? That is, if we make material, if we make something that is designed to recycle, and that I guess costs more money to do in effect, are we prepared to do that? Are we prepared to go to that length?
The thing is that I'm speaking as R&D, but as an operator, we are not directly buying the blade. It's more to the manufacturer that we have to ask that question. And then, of course, we will have to pay the price to operate that wind farms. But the first question, I think, goes to wind farms, to wind blades manufacturers.
Okay, I don't know if anybody else wants to comment on that.
I guess that maybe, sorry, Mie, countered by if there's any additional costs or fines or fees at the regulatory end products, which will work out better for the companies involved.
Yeah, okay. Sorry, Mie, did you want to say something about that?
I really think this is key, right? Because if there's a bill, someone needs to pay it, and it will probably be pushed around until someone, until there's no alternative. I think, Lorna, you said it here, right? If it probably will turn out to be the best and the cheapest option to go with a recyclable blade. I think the question is when will this be? because if you cannot buy a non-recyclable blade, this is yeah. But we still need to. I mean, we still need to compete with all the other ways you can buy electricity, basically. And this is a bit,
isn't it? The cost per unit of the electricity has to be competitive, and if you add cost to the manufacturer of the thing that's producing it, then that's pushed onto the consumer ultimately, and they don't want to pay more money. So yeah, I'm just going to move on to a question that's come from Darshil Shah. It says, I think the distinction between recyclable and recycled was important. Do we think extended producer responsibilities or directives, such as in the automotive sector, making producers responsible, so this kind of follows on from the last question, are necessary or will happen to ensure that blades are actually recycled and not only recyclable? So I think that's quite a good point there, but what do we think? I mean, I guess that really does follow on from the last question, right? So who wants to take that? Pierre, perhaps I'll go back to you again.
This is a good question for sure. The thing is that, sorry if I didn't understand well the question, but I think that the process of recycling of the blades will be somewhere decided by the material used for the blades by itself, as we have seen today in the presentations. Lots of different solutions are proposed. I mean, thermoplastics or thermosets with special resin that can be recycled by a chemical process. So finally, finally, we will be driven by that, and the blade will be recyclable by this process, and the recycled materials will be the one. The quality of the recycled material will be the one we're gonna get with the recycling process. Is it clear? Not so much.
Yeah, I think so. I mean, ultimately, it's going to come down to legislation, isn't it? Like the car industry, if the manufacturers of blades are then responsible for their end of life, not the users of blades, then that might push this down that route. In view of answering all the questions, because I noticed we've got just over 10 minutes left, but there's a question here from Alexander Ferguson. I'm going to do my best to try and interpret this, but if wind turbines were made using bio-derived resins, then would recycling be as important as atmospheric CO2? And then it would be effectively sequestered in the blades in such bioresins. Okay, so is that going to be the case?
Yeah, I think, I mean, no matter where we have our materials from, no matter the source, I think it will be a problem if we cannot handle the waste afterwards. I don't think we will ever be able to accept these graveyards with just end-of-life blades piling up. So I think doing bioresins, I think, is super interesting because it will efficiently put our carbon footprint very, very low. But I think still the recycling part is important. But just bridging that and what Pierre said before, I think there's another solution that is not just pushing producers or forcing them to handle this, but having a model that is more similar to what you see in steel. Because scrap steel, it's not waste, it's a resource. And if we can aim towards that, I think naturally there will be a market for this, and that will very efficiently solve a lot of the problem. It's much more challenging, it's much more technical, difficult, but I think this should be our sort of what we should aim for.
Yeah, I mean, my personal view is that if you use some bioresins are said to be biodegradable, and that gives, I mean, in the packaging world, that gives consumers the right to throw it away, right? So and that kind of puts an end then to actually doing anything else useful with it. So I think I think we have to look at materials that are useful beyond the end of life. So so cradle to cradle, if you like. Perhaps we could move on to the next question, which is, and I'm going to go to Lorna for this one. Okay, have you considered the cost of decommission and transport to the recycling plant, and that could that increase the costs of the recycling process?
Yeah, absolutely. It's a major question. As we've already said this afternoon, there's been no kind of large-scale decommissioning of offshore wind farms so far, but there is a question around where would be the best place to locate these recycling facilities, whatever they end up being in terms of the best answer. And if you can, do you take them straight from the wind farm to a port where the facility is located, or do you have to take them back to the port where everything's being decommissioned, chop it all up and then transport it by road or rail? There's a lot of discussion going on in that area at the moment across all of these aspects. And as I say, there's a lot of academic research going into reevaluating the full life cycle environmental assessments and cost assessments to take into account all of these aspects of all of the materials, and it's going to be a huge piece of work for people to come together on. And as Mie's already said there as well, there's a huge opportunity for job creation here. The argument over who's going to take responsibility of all the parts when they come back to shore, is it the operators? Sometimes wind farms are owned by multiple parties, the shareholders. If it's the original equipment manufacturers, then they know the equipment best. They would be possibly best positioned to advise as to how best to reverse process them, if that's the right word. And it's, as we've already said, it's going to be a huge collaborative effort here, and there's an opportunity to create a whole new supply chain of jobs here as well. One report was estimating out of the kind of recycling circular economy model for the whole of the UK, we could have hundreds of thousands of jobs. So an estimate down for the wind sector alone could be 20,000 jobs in the next 5 to 10 years just on recycling offshore wind.
Okay, thank you very much. Next question from Alan Hall. Which technology, I'll put this to me, which technology is more likely to be used first on wind turbine blades? Reusable or recyclable thermoplastics or thermosets?
Ouch. Well, it's difficult to say, right? Because it depends very much on the technology. I think there's pros and cons to both, and it's just a complex weighing. I think there's a big there's a big advantage for the thermosets, because this is what we use already, and that is what the production is set up for. So maybe this will sort of blend a little easier. But I think this is just a very high level answer, right? Because it depends very much on the technology and the analysis we will make to integrate a new technology like this will be huge, right? And we'll need to include all of these life cycle analysis steps. We'll need to have a very well controlled mechanical understanding of new material. We need to have a good process understanding of the materials. Yeah, so it will be a guess, but yeah, I think the thermoplastic, they might have an advantage end of life, but if it can weigh up all the historic material understanding we have, I think that would be a little difficult.
Okay, I think this is going to be our last question now. and it's kind of a sort of high level thing. I don't think it just applies to the wind industry. And I don't know who wants to take this. It might be you again, Mie, but what kind of barriers exist in data sharing for higher quality life cycle analysis?
That's a good question. I know that we share a lot of our LCAs already, so I will encourage people to look that up. It's readily available on our webpage. For the higher, I mean, of course, there are some trade secrets and whatnot in there that we might not be able to share all the information. Also, we have firm agreements with our suppliers. Maybe they cannot allow us to share all the information. But I know there's a lot of research going on in also opening this up, because every time we include a new material, this is the #1 question we ask. So for all our components, this is the evaluation we do. And therefore, it's also quite important for us to be quite open about this. So I'm not sure in the question if there's something specific that they were looking for, but as what I know, we try to share as much as possible.
Well, I think it's good practice to share LCA anyway. It's important to publish an LCA.
Yeah.
And then it's like a paper. It can be critiqued and
exactly
challenged. And I think all of that's really important. Okay. I think we're done on questions. I realise we've got 2 minutes left, and I should really hand over to Professor Paul Weaver now, probably to sum up the conference, and also just to thank our panelists as well in this last session. Thank you very much to all your answers and being so well informed about what's happening in the industry today. Thank you.
Thanks, Steve. Great session there. So it's just been a fantastic event, actually. The time's flown by, 3 3/4 hours out in the flash, and we've kept to schedule, so that is superb. The most important thing I really need to do is thank speakers and panelists today who've given up their time freely, and also to their organizations have allowed them to do so. We've had a spectrum of different opinions, largely in line with each other, which is, I don't think, too surprising considering the issues at stake from industry, academia, and also government organizations. I've been amazed by the breadth of delegates and where we've come from. We've got people in West Coast states up at some very early hour in the morning coming in live to this event, even though it's recorded and you can watch it at your leisure later on. We've had people in the Far East, we've had people in Africa, just about all corners of the world, which is fantastic. We're not going to change the planet now, but having these discussions is a step forward, and it raises consciousness. So let's keep going forward, and I hope people get a lot from this seminar and actually go back and can refer to it in the recorded presentations. Last thing I want to do is just thank the support teams, who the delegates are not necessarily aware of, but from ORE Catapult, particularly Anna Southall, and from Bristol, we've got Yida, we've got Heinau, we've got Catapult in Neva. Thank you very much for your contributions. Without your professionalism, this event wouldn't have run so smoothly. So with that, I think we're all done. Thank you again. And remember to look for the recorded presentations. You'll get a link to show where you can get them from. With that, I'll say bye-bye. See you soon.